Yeah, so if you could somehow use like a Windows technique, I know even in the Euclidean space, the short times can correspond to higher root S.
Right.
And,
The problem is if you try to localize an energy space, then things go crazy in Euclidean space. So you get big cancellations.
But I have seen this plot before where you take your 3 Euclidean time windows and you show
Yeah.
where they
Yeah.
show up in root S.
You can do that.
And so all we need is like a coarse sort of
Yeah. Well, that's
2-bin analysis.
That's also what I'm thinking, that, it may not be perfect, but maybe there's some. Or, windows.
Yeah, that can weight up the low root S.
Right.
And look at that area, weight up the higher root S. That area, and you put it that low.
Hey, how you doing?
How's it going? Morning.
Hello. Sort of based on this long distance window reconstruction, right? Because if if I tell you what all the whole tower of the base is.
How's it going?
Good.
I didn't remember if you, I didn't know if you remember me from.
Now we have to move the traffic.
Yeah, you were months ago.
That's,
Yeah.
no, no, I,
Awesome.
let's see.
Can I somehow get this?
Which has it, so I can walk it up.
2018.
There's benefit actually.
Oh, yeah, right.
Yeah, yeah.
Yeah. A while ago.
Yeah,
How
long
things?
time ago. Good,
Yeah.
I'm here now. Yeah, I just came here. I was at Michigan.
Right.
Okay. Yeah, this one's the, apparently much.
Oh, really?
Yeah. Yeah. Everybody back to their spots.
Yeah. all right.
Oh, let me show this one.
Yeah.
So you don't have to like
All right, good morning, everyone. Today is the day when we discuss Lepton flavor violation in all its forms, and we're extremely happy to open with the talk by Bernstein.
Thanks. Can everybody hear me?
Yeah.
Okay. So given this audience, I felt like idiotic talking about anything, but that's fine. I thought it would be interesting for this group to hear about sort of where we're going next and what might happen. And maybe there are some things you don't know already. So much of this talk, Bertrand ran a workshop in Caltech here, which I'm going to steal a lot of slides from. And I want to thank him and Francesco Reina at Roma and lots of other people. So I don't really need to do this, but I'm obliged to start. Why is muon charged lepton flavor violation interesting? So that's been around since the muon was discovered. And I think it goes to, really basic questions. Why are there lepton or any flavors? That's very basic. Muon charged lepton flavor violation probes mass scales of 100,000 TeV or higher. So this is from the physics briefing book for CERN. So you see that lepton CLFV is up here in the 10 to the 5th scale. Not much that competes with it. Some things that people usually don't talk about is we can study delta L equals 2 processes, and I'll talk about that a little bit, that are related to neutrinos. I'll also say a couple of things about muonium, anti-muonium oscillations. But I think we don't need to establish that this is important physics that P5 should promote. So, one thing that we tend to not advertise enough, I think, is the relationship to neutrinos. So, as soon as the muon was discovered, it was logical to think it's just an excited electron. And then even I can calculate this and get it's about 10 to the minus 4. But there were a bunch of really wonderful papers, and there's one in particular by Feinberg and Weinberg in 1958 that pointed out, and here's a clip from the paper, that says unless you're willing to give up the 2-component neutrino theory, that you get mu to E this, which you don't, right? You don't see mu to E, so you would see this, right? A 10 to the minus 4th if the new mu were equal to the new E. Okay, so that's been known since 58. And when I give talks on mu to E, I show that how this paper and all the papers that went with it just started this systematic exploration of neutrino oscillations until the Schwartz, Letterman, Steinberger experiment. So we're very closely related to that. And if P5 is interested in neutrinos, it ought to be interested in muons. All right, which we told them for 2 years during snowmass, and I don't know if they paid any attention or not. We'll find out. So the CLFV muon processes are mu to E gamma, which has the more powerful limits in the best experiment so far. Megan make it 2 at PSI, where they exploit two-body kinematics to identify a signal, proceeds through loops. There's mu to 3E, which you'll hear about later. Looks at 3 electrons, looks for 3 electrons in the muon mass. And there's finally mu to E goes to mu to E conversion, which mu to E and COMET are doing, where the signal's a monoenergetic electron, it's just under the muon mass. And so you hear about these experiments from these people. One important thing to keep in mind is that these are positive muon experiments because you want to stop them in material. And this is a capture experiment where you want a negative muon. And so that actually has a lot of ramifications experimentally. So the upcoming experiments, MEG2 just finished its first run, where they expect 4.2 10 to the minus 14th at 90% confidence after a few years. Mu to 3E, my understanding is that that first running will be 2026. This is a really nice paper. If you want to understand the experiment, you should read this. With a single event sensitivity down at about 210 to the minus 15th, and then us and COMET, which are in the range 6 to 810 to the minus 17th around the end of the decade. So this is new. This is new, and I think it's interesting. So Bertrand and Sasha Davidson, there's a standard Andre de Govia plot you show where you add 2 Lagrangian terms together in dimension 6, and nobody's happy with that, but it's really simple to understand. So they went one step further, and they broke it up into a bunch of different operators, and I'm not going to go into it. You should read the paper, which is here. But in the same kind of kappa lambda scheme, so here's lambda, which is the mass scale. Here's kappa, which is how much is sort of dipole operators. It's more complicated than that. This mechanism in EFT lets you put us, mu to E conversion, mu to E gamma, and mu to 3E on the same plot in a nice way. But the thing I want you to get from this is where we are now. Okay, it's sort of at about 1,000, couple thousand mass scales. And so the future, we want to go up here. Okay, so 10 to the 5th, and that sort of gives you also in the scheme a target for mu to 3E and mu to E gamma. So it tells you if you're going to make this kind of progress here, you should make this kind of progress here and vice versa. Okay, everybody needs to move together because we're indirect experiments. So one experiment, although it tells you, okay, you're going to Stockholm because you found something, right? But if you want to understand it, you need to do all 3 experiments. And so this kind of scheme that they came up with allows you to figure out how everybody needs to move jointly. So I think that's really nice.
What are the red dips in this plot?
Oh, that's interference terms.
I will talk about that.
Yeah, there's one slice, right? This is one slice.
Sitting on my stuff.
Yeah, and then it's all mad. So actually, I think we also need to say something about charge lepton flavor violation and tau decays. So just for comparison, so the good news is that beyond the standard model rates are an order of magnitude larger than an associated muon decays, or can be. But, you get 10 to the 10th taus a year, we get 10 to the 11th muons per second. And so there's just no way to compete, right? But there's another way you can think of it as competitive, and it is that muon charge lepton flavor violation is sort of the theta 1,2 sector in neutrinos. And anything involving the tau is the theta 1,3 or the theta 2,3 sector, about which we say nothing. Okay, and then the colliders can also probe Higgs decays, which I'm not sure you hear about. So this is a plot. People in this room made this plot. So in the mu to E sector, we just clobber everybody by 7 to 8 orders of magnitude. But as soon as you look at taus, we say nothing. And so this is a plot worth looking at. So upcoming accelerator improvements. At PSI, there's a high intensity muon beam. So Angela later will tell you about that at 10 to the 10th muons per second, about an order of magnitude improvement, which will provide significantly more beam for MEG and mu to 3E. At Fermilab, PIP2 can easily provide an order of magnitude improvement on mu to E. it can go beyond that. It can just give us as many as we can possibly manage with. The energy scale isn't quite set. It doesn't really matter whether it's 800 MeV or 4 JeV, anywhere in that range. It doesn't much matter. At J Park, there's a second target station planned. I don't know if Yoshi's going to talk about that. Similar rates to high intensity muon beam for a surface muon beam. And then we have an idea, which we call advanced muon facility that Bertrand will talk about later, where we just blow all of this out of the water and go a couple of orders of magnitude beyond any of this. So what might be the next generation of experiments? So here we need to look at the experiments themselves. Can they take advantage of these accelerator improvements? Can we use current designs with adiabatic improvements, or do we need a phase change? So this is my opinion. Looking forward, Mu-3E is an evolution and completion of the current design. Mu-2 or COMET kinds of experiments have an intermediate stage at PIP2, but to go past that, it's a phase change. You need a different design. I think that MEG needs a phase change. MEG people might argue with me, I'm not sure, but let's examine the experiments. So Mu-E gamma, so MEG or MEG2, anything like that. So the signal everybody knows is a mu going to an E gamma, so it's back to back. The electron and photon have the same energy. They're back to back, simultaneous. There's two backgrounds. Okay, one is radiative muon decay, where these neutrinos have basically zero momentum. It's about a tenth of this important background, which is the accidental background, where you have two decays in the same time window. Excuse me. And this electron and this photon line up. So this is the dominant background. And so once you know it's an accidental, you know it's going to be rate dependent. Okay. So in writing a paper, I actually had to derive this. So you see this all the time, and it's not a mystery equation. This is because it's an accidental. This is because the time difference between stops is random. Okay, and so in that last one I showed you accidentals, so the bigger the time window, the more accidentals you get. This term is from the Michel. Okay, this term is from looking at the radiative decay for the radiative decay of the muon. So if you look near the zero energy neutrino edge, it's basically a Brem term. It goes like 1 minus y dy. So you can integrate that out, and you find it goes as delta E gamma squared. And then for the last term, since the direction of photon is opposite direction of the electron, you get angular phase space that's delta theta delta phi, so you get delta theta squared. So this equation is not, this background dependence is not it's not a mystery. You can actually sit down and figure out what it is. But the important thing is that's quadratic, and these two are linear, and you're quadratic in rate, instantaneous rate to be precise. So why do you care about this? So if you look at the branching ratio versus beam rate, basically, I think they are going to head from an efficiency dominated regime to a background dominated regime. And then they need to do something about the accidental rate. So what experimental ideas are there? So if you look at the history of this, Mu-E gamma searches have gone back and forth between converting the photon. So conversion has a huge advantage. So the background, in this process, you have 3 tracks to make a vertex with much better, now you have a vertex, okay, which you don't in Mu-E gamma, where you don't convert. So if you have a calorimeter and a tracker, right, this is just a space point some distance away, and so you don't know where the vertex is, and then you don't know delta theta, and then your background's quadratically dependent on it, okay? Now, it's much more complicated than that, but at a cartoon version, that's what's going on. And so if you really want to push that delta theta squared term, you need a vertex. So rate, that was so Mega, which was the predecessor to the MEG series, this was the central problem. They had all these curl up tracks, and they couldn't reconstruct anything, and the experiment didn't go so well. MEG and MEG2 very sensibly did not convert, and they've done a wonderful job at much higher rate than Mega did. But then the moment you convert, you lose a factor of 100 because you want to have a very thin converter. So just schematically, you're going to lose, you're only going to convert 1%. But you want a very thin converter to minimize multiple scattering and energy loss, because you stop the muon, you let it decay, or you let it convert, or whatever. And then the same material that you used to stop it now provides multiple scattering and energy loss. And then as the track goes out, you know, okay, so now you're tracking it, but now your conversion material is giving you multiple, you know, all these bad resolution effects. So it's a trade-off. So my uninformed opinion is that the next generation of experiments in mu to E gamma should convert the photon. So I know people are thinking about this, but this is a very detailed experimental question. And I've got links to people looking at these things. So I know that the MEG people are thinking about this in conjunction with the mu3E people. So there's been a paper that's been going around for a while from us. My paper with Peter Cooper has the whole history of this. So more on the tracking, it's not the purpose of this meeting to discuss the details, but I just wanted to show you one plot from MEG2 where you can see how much, so this is 25% a year in red, gain loss from aging. This is 5%. So you can just see what happens when you go to these higher rates. So people are talking about gaseous detectors, silicon detectors, and multiple scattering before the detectors, just from the target, the gas, the detector walls is a limiting factor. So even if you do track, you know, life isn't perfect. So these are some, as an experimenter, these are some really, really interesting issues that say how far you can go and what your new techniques might be. You know, and then you could also rationally argue you should abandon all that and use photon calorimetry. So MEG's liquid argon could not get a photon resolution much better than an MEV, which is not understood. So they just put out a detector paper. This has implications for Pioneer. I don't know if Doug's going to talk about that. There are crystals that might give you 800 keV, but they're very expensive. You might get 30 picosecond timing, which affects that delta T E gamma term.
Wow.
Yeah.
One point about MEG detectors that when they built the large scale prototype,
Yeah.
they did get very good resolution,
Right.
but they didn't, wasn't translated into their main detector performance.
Right. Right. Yeah, you mentioned that to me the other day. Yeah. Thank you. You know, and then exactly if you do convert, right? So the first order momentum in a tracker is better measured than energy in a calorimeter. So where do you put all these converters? You put all your converters in the middle, you spread them out and have rings of converters. So people have been floating around thinking about this. But if we're really going to do this, we need to get serious. And there's also ideas of making active converters. So there was at that Caltech workshop, there was a nice talk about that. And I know that the MEG2 people are discussing what to do with high intensity muon beam.
What does it mean?
What?
What is an active?
The same, it's so you convert and you measure at the same, so you have, so a passive converter would be just a sheet of lead, for example. An active converter would be a silicon detector where you're converting the photon.
In the past, like radiative muon capture, we're doing conversion, right?
Yeah.
So it's the same.
Right. No, this is, look, this isn't, none of these issues, none of these questions are new. The thing is, for every generation of intensity and every generation of experimental beam structure, you need to figure out what the best answer is for where you want to go. So the first couple of slides, I tried to set up, okay, this is where we want to get, right? The next generation of experiments should be here. In order to get here with this beam intensity, what is the best design for the experiment? So I'm trying to show you that that's what we have to think. And we have to think about it as a community, because everybody in this, we're all in this together. And we need to move forward, you know, and think about what Muon CLFV needs to do. So Muon electron conversion. So to anybody outside mu to E and COMET, we're identical experiments. Okay. So I'm just going to use mu to E, but I mean mu to E and COMET. All right. And they're all based on Loewe-Sharp's idea here. And it's the beam design is driven by a very simple problem. Is the same pions that make our muons leave some undecayed pions, right? They don't all decay. And then you have this process called radiative planting. Star, and the gamma goes to E plus E minus. This can either internally convert or it can externally convert in the same material that's used to stop the muons. And sometimes that muon is is at the conversion energy. So that's a vacuum. So the way you get around this is have a pulsed beam. So you have a well-defined pulse. You take advantage of the pion lifetime to let them decay before opening the measurement window. And then you make sure there's nothing in between those pulses. Because if you have a pulse, so if you wait as long as we're going to wait, it's an 11 order of magnitude suppression. Okay. But if something comes just before you open your measurement period, that 11 orders of magnitude gets wiped out. Okay. So you need to have a very clean beam. That's called extinction. We need an extinction of 10 to the minus 10. Okay. So graphically, it looks something like this. And again, mu and COMET are basically identical. We have a 1695 nanosecond period. The first thing so let's imagine the beam is this nice clean Gaussian, which it is not. The first thing that happens is you get this enormous flash of electrons. So the protons hit the nucleons in the target. They make pi zeros. The pi zeros decay. Some of them make electrons. And they get transported because they have the same sign as mu minus. And for the first couple of hundred nanoseconds, all you see is this blast of electrons and everything's dead. Okay? Then you wait for that to be over with, and then the pions start coming in. Okay, and then the muons, and these scales are normalized differently. Then the muons start coming in. So you basically, and here's the muon decays. You wait for this all to be over with. Now, of course, we're not going to put a cut count experiment. These are all going to be distribution functions, and we'll do it properly. But if you just wait 700 nanoseconds, all of these are down enough that you can do the experiment. So for aluminum, where the atomic lifetime is 864 nanoseconds, we open it up at about 700. Now, why can't you keep going? So you'll hear from Bertrand that high Z is the next step. So this paper, there's a slight adaptation of the paper, of the plot that's in the paper, but this is and you shouldn't call this a branching ratio, it's a conversion ratio of to muons to at Z versus normalized to aluminum. So aluminum is at 1 here, titanium is about 1.7, and you start to see these really large splits as you go up to something like gold. And so there's physics in there. So for example, from this one paper by Vincenzo and Bernstein and Gino, as a function of sine theta 1,3, gold versus aluminum is a factor of 7, which even we can measure, right? So again, there's a tight linkage between charged lepton flavor violation and neutral lepton flavor violation, aka neutrino oscillations. Anna has written a bunch of papers on that. So the answer is we want to go to high Z. Okay. So what's the problem? Well, you can't go to very high Z. So I just set up a bunch of time telling you that you can't look for an electron or a signal early, right? So here in red is the gold lifetime compared to our beam pulse. Here's the titanium lifetime compared to our beam pulse. Here's the aluminum lifetime compared to our beam pulse. So there's no way we can do this. I remember when we were first discussing this experiment at Fermilab, we were, well, should we do this or this? And I remember our discussion was, we have no idea how to do this, so we shouldn't try to do this first. So we went with that. But the next step is mu 2 at 100 kilowatts. So that gets rid of an unpleasant background. Antiprotons evade the extinction. They just wander around. They have infinite lifetime. Actually, the measurement is 10.2 seconds. And they make it to the stopping target. They annihilate. They make lots of pi zeros, which then make signal electrons. Now, we can try to look for other signs of activity, but that's kind of iffy. So it's better to eliminate the background altogether. And so if you go to these lower energies, they're just gone. There's an EP conservation threshold at 5 JeV. When you put in Fermi motion, it's more like 4 JeV. So PIP2 would be below the threshold, and that background would be gone, which is nice. The other background, our target can't take times 10 more beam. Chris talked a little bit about this. The existing production solenoid may not work. The shielding of the superconductor might not be big enough. The beam path inside the production solenoid at a lower energy is different. You're getting a different part of the solenoid. We have a port for the beam to come out. That port will be in the wrong place. The cosmic ray veto, right? We would get one event a day from cosmic rays coming down from the sky and kicking out 105 MeV electron. We have to do an order of magnitude better on that. And then there are detector issues. So in the Michel spectrum, right? So now there's a recoil. So if a muon just decays here, you get the Michel spectrum. But if you're in your nucleus, you can recoil. And that induces this distortion, which Robert Safran and Sarnecki have written about. So you see this all the way up to the endpoint. And so the detector has to get better. So mu to E and mu to E2. So mu to E2 will go down to 8-micron straws. Minneapolis happens to be the world's experts on building 15-micron straws. But even that's not enough. There's a lot of other improvements. People have looked at this, and this is what they're thinking we can do. So the expectations are here for a mu to E2 5-year run versus mu to E, where you drop an order of magnitude in the 90% confidence limit. Or if you see something in aluminum, then obviously you go to titanium and you just run. 3 things I didn't talk about: light neutrals. So Ure will talk about this later. They come for free as calibration runs. These are really nice. There's delta equals 2 process, mu minus n to E plus n star. It's a simultaneous at mu to E. It's simultaneous in COMET stage 1. I believe they need a special one at stage 2. But by the Schechter-Valley theorem, this implies neutrinos have Majorana mass, which is kind of cool. And possibly 10 to the same 10 to the 4th improvement as we'll get in conversion. Something which goes with none of these experiments is muonium, antimuonium. So it's not lepton number violating, but it is doubly CLFV violating. And there are lots of papers on that. And I think in a bullet point, most experimenters think with modern technology, we can improve it by 2 orders of magnitude to 10 to the minus 5th G over G Fermi. So summary, all these experiments are going to break new ground. They complement each other. We're thinking about the next generations. I suspect qualitative phase changes will be needed to exploit accelerator improvements. But if any of us see a signal, we have to do all these channels. And sort of the way it feels to me, let's see if this works, is that this is what it's like dealing with funding agencies in P5. And you just have to be persistent. Okay. And remember what happens. He eventually climbs the stairs and kills everybody. Okay. So for questions, so Ure shared this chat GPT image of him, Ure. And I would suggest, this is so demanding and knowledgeable. I would suggest if you have questions, just ask him. Okay, thank you.
Okay, well, I guess you can ask the picture, but if you would like to ask Robert any questions now,
It's eventually. It's a bench question.
I guess you can ask yourself, so.
So this number of 1 in 100 for the sweet spot for the electron, so the photon conversion that you had for.
That's no doubt.
Yeah, so if you had an active converter, would that be a bigger number that you could? Like,
Maybe.
Oh.
That's a really, we don't know. That's a good question. That really depends, not to have a specific design and work through all the numbers. And but I think at this stage, we're not, is it worth it or not? How do you want to do it generally when you get a 2 map? That's the right sort of experimental question to be asking.
and you would know the plane of the E plus E minus, no? You would know, like essentially you would know the polarization of the photon through this. Would you? Like you would know that the.
The stock being demand is about 86% polarized.
Yeah.
I don't think that gets lost.
No, I mean from the E plus E minus that they
Oh,
convert.
sure.
Yeah.
Yeah.
Okay.
In the photon polarization.
Yeah. Probably. I mean, there's a correlation with the plane of E plus E minus that comes out in the photon.
So it's like a pair product, so that we can see in photon compact E plus E minus, it's pair production.
Yes.
So there must be some relation.
But you don't know, there's no preference for the plane. Inside.
No, I'm thinking of other processes where you could use this,
Ah,
not for the two body.
okay.
If you do something else, then this would be interesting to know.
So just out of my curiosity, for the mu minus to E plus, presumably I should be thinking about this is coming from some model that you integrate out a Majorana neutrino or something.
Right, so I have a whole talk on this, which I can show you the slides for that.
What did I just a very rough idea though? What's the time of what kind of mass scale that we're talking about? You can probe with this.
Um. So, okay, that's a good question. I don't have a good answer.
Probably depends on the company.
Totally depends on.
But does it plug into some out of box neutrino mass model?
Yeah, no, so what theorists usually say when I talk about this is, oh, well, since you don't see neutrinos double wave decay, this is, anything you would see is ruled out. But then if you look a little bit deeper in the papers, there's lots of models where that doesn't apply to this.
What kind of weird things?
I'll show you later.
Okay.
I just want to establish that normally we don't talk about this, right? And I think there's actually, it's very hard to experiment because that can proceed either through the final nucleus is in the down state, or it can be in a giant dipole resonance. If it's in a giant dipole resonance, there's no good model. So we really can only look at the delta of the ground state, which is estimated to be about 60%. And then there's a question about what the radiated muon decay background underneath that is. If that's the background for this. If you look at what's called the Lepton approximation, which prevailing here, there's 0. But there's some kind of mixed evidence from trying that there's a long trail underneath that, but nobody understands. So one of the things we want to do is measure that.
Bob, the extinction 10 to the minus 10 presumably is measured in a separate experiment. But do you have a method to monitor it on a burst by burst basis during the experiment?
Yeah, that's
running.
So we have, so you asked me about it. So downstream of the production cylinder, there's a little spectrometer that can measure the extinction on the order of 8 hours. Then we have that AC dipole, right? So in the beamline, there's a dipole that oscillates such that when the beam comes through, it doesn't deflect the beam, and then it very quickly sweeps anything out. Okay. So only an idiot would design an experiment that didn't measure immediately before and immediately downstream what the extinction was. Well, because the project didn't have enough money, we didn't design it. So we are building an upstream extinction regime that will get a sort of pulse by pulse before the AC. But then the AC dipole knocks it down 5 or 6 orders of magnitude. So we'll measure it before, on a very quick time scale, we'll measure it afterwards. We'll also measure pulse by pulse what the total activity is by looking at the calorimeter. So that's the best we can do. It's the fast measurement pulse by pulse upstream, and then once a shift downstream. If we see something before the dipole, like we'll immediately stop. After the dipole, you just drop by 6 orders of magnitude, so it just okay. And then you could put something immediately downstream of the dipole, but then you also want something that actually looks at the target, right? Which is what we designed.
I guess you already partially answered. So the among the backgrounds you mentioned this decay in orbit where the 2 neutrinos are very soft. But if I kind of go down, there is also radiative muon capture, right? Where there is only 1 neutrino, but then the photon would be separated by the binding energy, whatever that you have to do to convert one of the protons to neutrons. The question is this separation enough from the experimental point of view to see?
It's
okay.
What it does do, okay, which is really interesting. So this DIO action, so Anjay and Robert calculated this. So we put this on our mind always and say, okay, there's point 1 event that. And then, of course, you measure this. Right? And if this doesn't agree with the paper, then you say, well, how can I possibly make this extrapolation? And radiative muon decay can mess up this region. Okay, so we have to understand that, so we understand this, so we can believe our extrapolation under our signal. So that's where radiative muon decay comes in, is in our measurement, our understanding of the DIO background.
Okay, yeah, I think we can take one more question.
You had a message that mu2 gamma, mu2 and the mu2 conversion all should be done in the future. In the
I'm not gonna argue with that.
yeah, but from the figure you showed me, I think my impression was that you should push mu2 conversion rather than other things. Isn't it?
Let me show the slide and then you can,
Yeah.
okay, so what on the slide are you asking about?
Yeah, so the red line is the mu2 conversion.
This-
That, yeah, that's much better than anything else. So that.
Well, cool.
Yeah. So okay, that's a good thing.
Yeah, but it depends. So again, it depends on what kind of physics you think you're doing. If it's dipole bound, right, then mu to E gamma and mu to E conversion are about the same. Okay.
So dipole don't is the same trouble.
There are a few caveats, but
Yeah, but let me give them the big picture. And you can figure it out. So right now, I understand, right, Meg and mu to E conversion and mu to 3 are all about the same for Susan. But if you're talking about exchange, like a Lepton force, then they can't see that at all. Okay. So you can imagine they see a signal, we see a signal, okay, it's a loop. They see a signal, we don't see a signal. But that couldn't happen. We see a signal, they don't see a signal, it's a contact.
Yeah, of course. The many measurement gives you more information. That I understand.
Yeah, that's the point.
Right. Okay.
All right, let's thank Robert again. All right, next up, Yoshitaka Kuno will tell us about
Okay, can you hear me? Well, first of all, thank you very much for invitation. It is my pleasure to come here. This is my first time. So, my name is Yoshi Kuno from Osaka University. And I'd like to talk about the search for Muon electron at COMET experiment. So, okay. I was just told that I can use the PowerPoint. So my slide has some animation. Try to entertain slightly more. And then also I have a lot of slides. I hope that I can finish within allocated time. So, okay, so this is outline my talk. So I like to talk about what is a MIWI conversion, and then mention about the COMET experiment, and then I'd like to talk about some future if I have the time. So let me just start from why we are interested in that charge lepton flavor biotic physics. So one of the reasons is, first of all, this charge lepton flavor violation has a very clear signature of new physics beyond standard model. Since the standard model contribution is negligibly small, like a 10 to minus 54. So if we found a signal, so that indicated clearly, definitely, that's a new physics beyond standard. And then secondly, in the PFT framework, now charge lepton flavor violation reach already that physics scale of new physics over 10 to the fourth TeV, assuming that the coupling constant order 1. And then upcoming experiment will improve this physics reach by order magnitude. So in the dimension 6 operator, this rate is given by 1 over the lambda to the power of 4. So that means that we have to improve the experiment sensitivity by factor 10,000. So that's challenge for experimenters, but then that is how we are working on. Now, in the EFT framework, the mu conversion can be discussed, studied in two, in a contact interaction and then a photonic interaction. Because it's a mu conversion involves a quark or nucleons in the EFT, therefore, in the contact interaction, a possible operator is a main, like a scalar vector, pseudo-scalar, axial vector, and tensor, and so on. So that is a big difference between mu2e gamma or mu2 So the mu conversion, we have lots of possible operators involved. And then among these, scalar and vector is spin independent, and then the pseudo-scalar, axial vector, and tensor spin dependent. So this is a good analogy of direct dark matter search. If you know that the direct dark matter search is almost similar, so that there is a spin dependent and spin independent contribution. And then we can do the similar thing in mu conversion. And then this operator is independent from, in principle, different from proton and neutrons. So that we have to determine all this contribution differently. And then it was suggested that we should look at all different targets where this ratio of number of proton over number of proton is strongly different, so that we can discriminate contribution from proton and then neutron and so on and so forth. And then the photonic interaction. So the famous one is dipole interaction. This is like a mu2e gamma. And then recently we have also the two photon contact interaction. This goes like a mu e to mu e ff contact interaction. And then we also study that contribution to mu e conversion. And then you can expect that a very strong Z dependence compared to mu2e gamma. So if you have a mu e ff contribution. But anyway, so that to discriminate all these different operator, we have to compare different target and hopefully different ratio of a number of proton and neutron. If we started from right nucleus, we have to go high Z or like a lithium. And then we can discriminate all these contributions. So that's sort of idea. Okay, now experimental side. So what is a mu conversion? So we have a mu minus and then stop in the material to form a muonic atom. And then there is a muon either decay in orbit, we call the DIO, or captured by nucleus. So that is a standard model allowed process. And then we can consider like electron emission, no neutrino, new emission. So that is mu conversion. And then the experimental signature is that since we cannot see that what happens in the nucleus, we can only measure that monoenergetic electron coming out. And then energy of this electron is given by it's like a two-body kinematics. So the energy of the electron can be defined in this one. In particular, aluminum, its energy of like 105 energy. So this is very close to the muon. And then suppose its final state is a ground state. Namely, if this initial state nucleus and the final state nucleus is the same, and then you can expect that the coherency, and then its rate is enhanced by number of nucleons. So usually the muon capture is like a Z to the fourth power, but now if there's a coherence applied, this has to be goes to the power of the fifth. So that is a good point of the mu conversion. Now, the conversion rate is given by some normalization about the total muon capture. Now, this data from kappa, it's sort of a work of Doug's PhD work. I just quote this one. Anyway, so let's see. And then we have a lot of background sources, which Bob already mentioned. So one of them is muon related. So this one is the bound muon decay, where this endpoint of this bound muon decay electron is come very close to the signal region. So that is one of the important background. And I'm sure that there are a lot of 100 MeV electron in a beam, and there are lots of sources, and they have to be eliminated some way. And then the cosmic ray background was very critical source of the background. Now, having said this, so So I'd like to talk about how this mu-E conversion experiment looks like. And then, as I told you, that we like to aim at the factor 10,000 improvement. Now, to do this, we need a lot of muons. So how we can make a lot of muons? So one idea is to use a pion capture system where this proton target is surrounded by a superconducting solenoid with a high field, so that all the pions from the proton target were captured by solenoid field, and also the muon from the pion decay also captured by a solenoid field, and then provided to the experimental hole. So that is a basic idea. And then from simulation, we can expect a 10 to 11 muon for 50 kilowatt proton beam power, or one SS years, we can accumulate 10 to 18 muon in total. Now, we need some experimental demonstration. By the way, it's a previous experiment, 10 to 14 muons. So you can see that the 10,000 improvement number of muons. And then we need some experimental demonstration. So we made this pion capture system at Osaka University. So we have a very small proton cyclotron. And then that is a facility called Music. It's around 2011 time. It's a long time ago. So you can see that this proton beam line, and then this pion capture system. And then we measure that how many muons we obtain at the 400 watts. We get 10 to 8 muon per second. And then you can just compare to the PSI muon rate, like 10 to the base 1.4 megaohm. But just scaling this 400 watts to 50 kilowatt, which I mentioned, and then this 10 to 11 muon per second is obtained. So in terms of the number of muons, it's okay. Now, we have to also look at how we can remove the background. And then beam-related background, we can eliminate by proton beam pulsing with a separation of 1 microsecond. As Bob mentioned, that there is a leakage of proton between the beam pulse, has to be very small, like a 10 to minus 10 level. And also any 100 MeV electron source in the beam line has to be eliminated by curved solenoid, which I mentioned in a minute, in the momentum selection. And then decaying orbit, we have to have a very good momentum resolution of electron detection. So that needs a good tracker and also thin target and vacuum and so on. All these ideas came from this Merck proposal in the most Mason facility. So it's in 1992, it's Rashid Jirkibaev and then Professor Robashov. They proposed this system. It's called Merck. Certainly this didn't work. And then afterwards in the United States, there's a Miko proposal to the Brookhaven National Laboratory. And it's again terminated in 2005 because of the NSF budget issues. Then I was in the Miko, and then after this cancellation, so there are two experiments. One is the United States, and the other in Japan. And then the one in Japan is called COMET. Okay, so this is how this COMET experiment looks like. And then, by the way, this COMET stands for coherent muon to electron transition. So we use HGB and 56 kilowatt. And then I said that already 10 to 11 muon, stopped muon is expected. And then we are aiming at a factor 10,000 improvement of sensitivity compared to the syndrome previous experiment. We have a proton beam and then hitting a proton target in tungsten, and then we have a pion capture system here. And then we have a 180-degree curved solenoid for muon beam line, and then this aluminum muon stopping target. And then we have again that 180-degree curved solenoid for electron spectrometer, and then detector follow. This is a slow chamber plus electron calorimeter. And this is a JPAG. So we have a 3GB ring, and then it's the main ring, and then a proton beam extracted to a Hadron experimental facility where this COMET experiment will be accommodated. Okay, now, so we need a pulse proton beam with say 1 microsecond separation. To make this one, in the main ring, we fill this proton every other RF packet, and then this separation between two pulse is about 1.1 microsecond, and then keep this pulse structure and make a slow extraction. So that is how we can make. And then we already tested this system. And then we use aluminum target, as Bob mentioned, its lifetime is about 864 nanoseconds, just fit into the 1.1 microsecond repetition. And then also we have a delayed time window. As Bob mentioned, that we have to wait until this pilot, which stops the muon stop target, decay out. Otherwise, we have lots of problems background. So that this measurement windows are open after, say, 700 nanoseconds up to 1.1 microsecond. And then you need a proton extinction, as Bob mentioned, that we have to control this leakage between the pulse at the level of 10 to minus 10. And then this 10 to minus 10 already verified at the JPAC. We measure that proton extinction in a test experiment, and then we already verify this. So we are just constructing some monitor system to check this extinction factor. Now, this curved solenoid with a dipole field. This is a very important component in the COMET experiment. So I like to mention this one. So in a uniform solenoid, you know there's a helical trajectory just going on this solenoid. But once it's a curved solenoid is curved, and then this is a helical trajectory, a center of a helical trajectory shifted up or down with respect to the bending plane. And then this amount of the drift is proportional to momentum over charge, so that we can use this effect to momentum selection or charge selection only. And then if you apply further dipole field along this drift direction, we can make some offset of this shifting, so that we can keep this particle of the momentum interest stay in the center of the solenoid, and the other drifted out. So that's a very important component of the COMET experiment. So in the COMET, we have a 108-degree curved solenoid in a muon beamline, and then another 180-degree electron spectrum. So what this 108-degree curved solenoid in muon beamline does, select a low momentum muon. So eliminate all these 100 MeV electron in the beam coming from the upstream. Those are all eliminated. And then this after the muon stopping target, we have another 180-degree curved solenoid, which select the 105 MeV electron, which we like to have. And then all these neutrons from neutrons and gamma ray will not come to a detector. Also, there are a lot of protons from muon capture with a positive charge. So they are also removed. And then also we try to eliminate all this DIO background from the signal, which I'd like to show in the next slide. So if we apply, say, a dipole field like a minus 0.22 Tesla, so you see this is a sort of a vertical position, and then this is the distance from muon stopping target along this curved solenoid. So at 105 MeV signal electron, stay the center of this solenoid, as I told you. And then the 50 MeV DIO electron are shifted down, and then we see that the difference. And then if you just show that the XY beam stop at the end of the spectrometer, so that the signal stay like this one, in the center of the solenoid, and then 50 MeV electron come down here. And then if you put some collimator, and then we can just easily remove this one. Now, the size of this beam is determined by a solenoid field, and then amount of this difference of a drift is determined by a bending angle. So originally we saw that 180 degrees is enough, but then it seems to be that 180 degrees may not be enough. But then at this moment, the experimental hall COMET is limited, so I cannot extend it more than 180 degrees. Presumably it's okay. But if it is more than 180 degrees, and then this goes to further down, and then we can easily eliminate. So that's how this electron spectrometer works. Now, we took some stage approach in 2016. So we tried to make only first 90-degree curved solenoid, and then put a detector, and then do some measurement. The original purpose was early realization, but then the project is delayed, so that early realization didn't work. However, we are still working on this. So we have HEV and 3.2 kilowatt, not 56 kilowatt, and then sensitivity is about factor 100 improvement compared to the previous. and then the running time is less than half year also. So that is COMET phase 1. And then let me just talk about the status of the facility. So all this experimental hall is already made, and all the cryogenic system required is completed 2021. And then we also need some new proton beam branch, which for the C line. This is also completed in 2022. And then superconducting magnet. We have a pion capture solenoid. The coil is ready, and then the cross stop is ready. And then recently we found that this magnet has a ground fault problem. It has been fixed this year. And then also Muon transport solenoid. Originally, it's go up to only a half of the goal, like 1.5 Tesla. But now this year, we made full excitation of 3 Tesla eventually. Detector solenoid assembly is ongoing in the factory, and then will be delivered to JPark sometime next year. So the detector, we have 2 things. One is a single chamber to measure Muon conversion at the phase 1, and then the other one is straw chamber plus electron calorimeter, which is for measure the beam profile, and then plus is a prototype of phase 2. So I have to go quickly, and maybe I'll skip this one. But it's a cylindrical drift chamber, has a large inner bore, and then it's a helium-based minimized molecule scattering, and all stereo layers make to drift chamber. It's already completed. The construction was made by Osaka University, and then I had China, and then right now sports nuclear test underway at JPark. It looks like this one. And then straw chamber is under construction like this. And maybe I just go quickly. So electron calorimeter also this riser crystal, and then this all this requirement met by this prototype test, and it's assembly underway at the Kyushu University. Okay, so I said that proton beam is already ready, and then we made proton beam commissioning. That is called phase alpha, and then we have this is a sort of phase alpha setup. It's a proton beam comes in, and you can see that Muon transport solenoid. We don't have any pion capture solenoid, but then we put a temporary proton target. This is like a 1 millimeter thick graphite, and then we don't want to make this area activated. So that's a very small beam power, like a 260 watt beam power, and then we measure all this secondary beam, and then also proton beam. We measure the size, like a horizontal is 2 millimeter, and then vertical is 3 millimeter. And then this is this is the experimental area. So we measured Muon range distribution, time distribution, intensity distribution, XY distribution, and so on and so forth. February 11th this year, we have a first observation of a Muon beam at the experiment area. So that's one of the milestones. And then data of the phase alpha is still under analysis is undergoing. Upcoming schedule that we will have engineering run start expecting early 2026, starting from very low beam intensity, and then go up to design test. Now, KK has a big budget problem, and then it may affect us, and also potentially we may also further delay can happen. Anyway, so that is the situation. And then presumably after the break, can we talk about the MUD2, I believe, so that I have to mention about that kind of things, so that we also are thinking that how we can improve further the sensitivity beyond the phase 2. I call it the phase 2 plus. So idea is that one of the PhD students working on its idea is that the increased number of Muon stop by changing target size and proton target size of a proton, and then also Muon stopping target, and then also signal acceptance can be adjusted by collimator, which I mentioned before, and then a slightly longer running time, and then we can achieve like 7 times 10 to minus 18, 90% confidence. But background is a 0.6. This needs some more investigation, but then that is sort of preliminary stage. Okay, so what kind of other physics topics can be done? Bob already mentioned that the mu minus E plus conversion, and certainly this is the Lepton number violation and then a charge Lepton flavor. I don't think this, we have only 10 to 18 muons. Therefore, that we are not sensitive to like long distance effect, like right minor neutrino exchange. So in this case, right minor, it's off diagonal, but effective neutrino mass. You know, I don't think we can compete with neutrino double beta decay. The only thing we can do is a heavy particle exchange, like a TeV, Lepton number violating physics, which is sort of comparable to what LHC is doing. Now, signal event, we don't have any coherency, so that maybe half of them is the ground state and half of them is excited state in the final nucleus. If you pick up the ground state transition, it's monoenergic positron, and then energy is given like this one. And then background, as Bob mentioned, that is a radiative muon capture, and then is a photon convert to E plus E minus.
What's the mass difference between the aluminum and
endpoint
this,
of
sodium?
I would say that in the aluminum case, I think it's an endpoint. I don't remember the nuclear mass, but then endpoint of the RMC is higher than a signal region. So that sense, aluminum not so good. But anyway, so that the current limit is given like this one. In a phase one, we can measure the electron position at the same time, so that a measurement has to be done in aluminum. Now, phase two is a dedicated experiment, so we can sort of choose some good material, and then something that the good target material has the requirement like signal energy has to be greater than RMC endpoint. So that puts some requirement of mass. This is like a neutronless double beta decay for similar things. And then we can just scan what kind of a nucleus meet this requirement. Not so many, one of them like a calcium, but then certainly the calcium is a nightmare for the experimenters. But nevertheless, it's one of the students, someone study all this simulation, and then this is summarized in PhD thesis in Osaka University. And then also the radiative muon capture is very important issues. Right now, it's all the measured endpoint of radiative muon capture is about 10 MeV smaller than kinematically allowed maximum endpoint. So I saw that maybe majority is 1 nucleon emission. Therefore, that there's some 10 MeV difference. But then certainly that there must be some contribution at same level. So we have to measure that this photon spectrum. And then idea is that use the CDC as a pair spectrometer. So if the photon comes and then convert at the inner wall of the CDC, and then we can track this E plus E minus to reconstruct the photon energy. So that kind of study already made by Dorian. This is summarized with a PhD work. This inner wall of the CDC is very thin. This is a purpose. So that photon conversion rate is not so great. But nevertheless, I think we can improve that previous triumph measurement of RMC, or we can think about some special ramp where we can put dedicated photon converter inside the CDC. So that's also possible. Okay, now we can move to one of the things. It's a mu2EX. I don't know, there must be talk in the afternoon. It's X might be invisible neutral particle is a flavor violating coupling to the electron, and then this is categorized by characterized by a decay constant of X particle. There are many experiments in the past, and then there are many new proposals made and then mu3E. And then a COMET we can do is a bound mu minus decay to E minus and X. So it's go like this one. So one of the problem is mu plus 2 E plus X. If this mx mass of the X is massless. Now, I like you to look at this dashed curve. So in this case, is the peak of this E minus X comes onto the edge of Michel spectrum. So in this case, it's very difficult to identify this peak if you come to the edge. Now, if you use a bound muon decay, so that the muon is moving, therefore this peak is broadened and then shifting. Amount of the shift is smaller for two-body decay, and then the three-body decay, amount of the shift is larger. Therefore, it's a Michel edge is normal overlap in this signal region. So that allows us to look at even massless X. So that's advantage. And then if we change at the target, the spectrum change, it's another systematic control. Disadvantage, many, is not more energetic, and then all this backward distribution has to be understood. Like a DIO distribution, also radiative muon capture. That's why we have to measure those radiative muon capture spectrum, and so on and so forth. So the preliminary study was made by a Chinese group, and that shows a very aggressive the decay constant of X particle is a 10 to 10 GB and so on and so forth. Okay, and then I don't know, you mentioned this one, but then it's a calibration, you don't. Calibration now can be used for such. So, okay, stop. Let me just do a couple minutes. So I like to mention that the long-term future, aiming at, say, 1 million improvement. So what we need is a beta muon beam. So one is a narrow beam energy spread, like a phase rotation, and then small beam emittance by cooling. This is, you can see that this is inspired by muon collider R&D. There is a synergy of a muon collider R&D. So let me talk about what is the phase rotation. So this is a muon produced by a proton pulse. Then the high energy muon comes earlier, and then slow muon comes late. So we have this time and then energy. And then if you apply the RF electric field, and then we can rotate, basically at decelerate high energy muon and then accelerate slow muon. And then eventually we can make energy spread narrow. This is a phase rotation. In muon collider, it's a phase rotation that right before a muon cooling. And then the second requirement is that, as Bob mentioned, that you have to have a capability of a high Z muon target. So this is shown. This is original work is Kuno-san, it's a PhD work. So we need early starting time of the measurement window is needed. So we have to wait at 700 nanoseconds. That's ridiculous. So reason is that we have still a lot of pion in the beam. So we have to wait for all the pion to decay out. So to eliminate all this, we need maybe long beam line, like 100 meters. Then I think a surviving rate of a pion is down to 10 to minus 20. So that is needed. Now, I set a two requirement, and these two requirements can be met by just using muon storage ring. And then we can, the circumference is like a 20 meter. It's small ring. And then just a 5 ton, that makes 100 meter flight length. And then we can put some, we can put some RF during this storage ring. And then, okay, let me go on. So we did some R&D study, this storage ring. So we use fixed field alternating gradient synchrotron, FFA, which Chris mentioned that yesterday morning. So this FFA is very suitable for creation of low energy muons. It's a large beam acceptance and then very fast acceleration because it's a fixed field and then synchrotron oscillation. So we made that FFA at Osaka University. This is a scaling FFA and DFB triplet, and then it has a very large field gradient, so that even muon is accelerated or decelerated, the orbit is not much changed because there's a high gradient. And then we made a ring like this, and then estimate that beam acceptance also did the phase rotation. This is summarizing one of the master thesis with the student area. So that was done long time ago. So I'm very happy that many people interested in this kind of project and then continue. I'm already very senior, so if the other people is continue this project concept, I'll be very happy. Now that brings me to the summary. Okay, so that Muon converter is one of the important Muon charge lepton flavor variety processes. So phase 1 is aiming at a factor 100 improvement. Phase 2 is a 10,000 or maybe 100,000. And then for 1 million improvement, maybe threading will be useful. So this is my dog, Iku. This photo was taken when she was young. She came to me slightly after I started the COMET. Now she's 13 years old and then coming to the 14 years. Okay, I stop now. Thank you very much.
All right, we have time for maybe a couple questions.
Yoshi, what experimental measurements have been done to establish the cosmic ray background level?
You measured also.
Not 10 to the minus 17.
Yeah, but then it's just a proportion to running time. How many days you are running? You're telling me. And then we are phase 1, we have only 150 days.
What about for phase 2 or phase 3 proposal?
Oh, this is 1 year. So it's not big difference. But certainly these days we have lots of simulation. And then we have also data over cosmic ray at the level of the ground, and then use all this information and make a lot of simulation. That we are doing.
It's primarily based on simulation. Not,
no.
not measurements.
Eventually, that if this detector is ready, then without the Muon beam, we can measure that's a cosmic ray background. So I think in principle we can have some control of background. We don't need any Muon, just a running experiment detector and see that how many background events coming into the detector.
So that's something to be done in the future.
No, before the experiment starts.
Yeah. Okay.
Before the Muon beam, I think we can do. I mean, having a Muon beam take a long time, but then measure the cosmic ray background easy once the detector is ready.
So for these mu2EX projections that you flashed,
yeah,
can you comment more on the backgrounds that would come in, and also about the acceptances that they had to assume for the low energy?
So background is many, so that the DIO and then radiative muon capture and so on and so forth. So we have to see all the spectrum one by one. So that is a very difficult, challenging task. But we realize, and then I think a paper made by this IHEB group didn't consider all this systematic error of the background. So I would say that this is very aggressive. But in the end, I think we like to study all this background shape. Hopefully we can measure DIO spectrum plus radiative muon capture, and then include this as the background shape, and then do some analysis. Yeah. For the acceptance, as I told you in phase 2, we have a signal and then a DIO background at the end of the spectrum. So between these two is all the charge particle between 50 to 100. So basically we can measure. I don't know where we can put the collimator, but then depending on this collimator position, we can sort of determine that sort of momentum range of this electron. And then acceptance, I don't remember, but then it's written in the paper.
So you can go all the way down to 50. I think they had the one choice, which was 50.
Well, if you go to the 50, we have another technical problem, how we can take a data.
Yeah.
So I don't think we can go to 50. I think it's slightly above.
And this thing that you can't go over 180 degrees, I mean, would you need to, you would need to build an extension to the hole to have a more than 180 degree?
Oh, in a COMET phase two, I don't think this area is determined, so I don't think we can add extension. But in a future experiment, it should be considered more than 180 degree or more than 360 degree, where this detector looks like a Guggenheim Museum lamp.
Okay, maybe we'll make this the last one before break.
Yeah, I could probably take this outside, but Doug, so your question about cosmic rays. So we in MUTE have used both Corsica and Diabae. And that's not really the issue. So the experimental issues are the dominant cosmic ray backgrounds turn out to be from cracks where we need to put holes so that we can get the cryo in. Okay, so Corsica versus Diabae, we don't care. It's not a problem. The few cracks that we have to have are the things that are actually the problem. And the other thing that's the problem is measuring the dead time. I mean, when protons hit protons in a target, you make neutrons and pi zeros, right? The neutrons deaden the cosmic ray veto. Okay, so knowing the dead time of the cosmic ray veto is a big issue that we have to understand carefully, and we can only measure in situ when we're actually at the experiment. And I'm sure Yoshi et al. Have exactly the same worries as I do.
But I think you can just run the detector without the muon beam, and then we can measure all this.
You can't measure what's actually there when you're taking data. You can't. Yeah, I was just gonna say you can't actually measure the flux, right? Until you're taking data, you can't see what's there.
No, it's just the proportion running time. So that's.
Yeah, but you need to see how many neutrons are hitting your counter and how dead you are.
Neutrons, you mean?
Right,
Okay.
right.
All right, great. Let's thank Yoshi again and then take a break. I guess let's come back at 11:05.
Since we are going to be watching the afterwards the presentation, we should take a break for 15 minutes. Be back at 11.
Yeah, let's start at 11 again.
Concentrate back then.
Hey, hello. How's it going? Good. Yeah. Yeah, likewise. Yeah, well, yeah. Well, it's 2 flights. I heard it was pretty good on the. But the usual is a result in
Yeah, so I was calling.
No, I arrived
Back in Berkeley, they were excited about it. So they're very pro Muon collider, so that correlates.
Yeah. I wonder what
Completely different issue. That's what we have to look at. We measure
For a while and do this for conditions.
Yeah, but that's probably, okay, I don't know whether that means anything.
I heard that they killed off Matilda and the Ford.
Whatever kind of background those,
The what?
those appear.
And the Ford
We
physical
won't be,
ability were killed off.
maybe you'll see.
Okay.
So that's all.
There must be a.
My favorite thing that just
You'll know-
for
You'll
physical.
know that there's a.
I know I could kill something. As far as the US.
Same thing with
Maybe Europeans. will-
Yeah.
If the extension fails or partially fails.
But those are small.
Occasionally, you'll have.
Well, I mean,
background.
yeah, there's a-
Not
I mean, FDS same.
But it's, I mean, it's actually about the monitoring the extinction and pulse like pulse basis. And you have something that looks at the target.
Oh.
No, we have last time, proton beam only. Just look at the hello beam.
Yeah.
But I don't think bunch by bunch is very difficult.
Right.
Yeah.
Okay.
I think you see it something.
Okay, yeah, so they're.
Sure. Is it sensitive enough? You have literally 8 or 9 protons per first hitting the target. Is it possible to have something looking at the target and that to monitor?
Good.
Many parts. But that's the beam itself.
Yeah, beam itself.
But if you have something looking at the target,
to see pions coming out of scattered
If you
protons,
have the link,
you might have enough efficiency
maybe we should just pull it up on this one. Or I mean.
to
we can
know
switch
that
your
there's
laptop.
something.
Oh, yeah.
There must be some links to this. The question is, because if you see a signal, well, you'll see background, and then you'll be cooked.
You can actually put it in the chat.
But I guess
Zoom.
there's nothing that
Oh,
will
no,
produce
never mind. This computer, no.
Yeah.
So if you have a make a peak at 105,
Yeah, then you're okay.
then okay. But
But
then
then
just a
if
distributed.
you have a background,
It's just a
like
link.
square root of n.
Yeah, it's just a link, you can email it to yourself or message yourself on.
Thank you so much.
So,
Very elaborate slides.
Or yeah. just do
So
that.
not
Yeah, that might
to
be
dig any skeletons from Triumph Closet, but radiative muon capture on hydrogen was discrepant like order 1 from the theory prediction.
yeah, I was not involved.
Yeah, I know.
They took over our beam line.
So
But you think it's interesting physics in the radiative muon capture? And then we are
it's in the end chiral perturbation theory,
Yeah, yeah.
right? So
Yeah.
Peter, Kamel, and others have later done this, not the radiative, but ordinary capture not in liquid hydrogen, but in gas, right? Where the molecular issues are not coming in, and they saw like perfect agreement with the theory, right?
Yes.
And so this radiative capture remains like, okay, what's going on, right? So if you have lots of muons in principle, to do this in gas, then you will remove this what is this molecular state, rate, formation, because there is always that uncertainty. So if you have enough mu minus, capture it in sort of a gaseous hydrogen and measuring the relative rate if the number of muons allows.
Yeah, maybe just one day special.
I don't think it's gonna be a 1 day. It's gonna be somewhat of a dedicated measurement, and then you could resolve that issue that's been around since mid-90s.
Yeah, 90s.
Mid-90s.
Unless there's some new physics with a heavy target.
Yeah, well, Triumph, they were doing lots of different targets, but if the precision measurement you can where you can calculate things with white hydrogen. Yeah, but because Triumph has not as many muons, I suppose, as you will have, right?
One day.
They were had to do the stopping in liquid hydrogen. Right? So if you can have intensity large enough, I don't know.
And then low pressure gases.
The pions are also a problem for those old measurements because they also tend to be important for so on. So it was also important for them to have like extinction of the pions, right?
Another discrepancy, there's this guy, Pablo.
I can just send you,
Murat?
Yeah, who looked at the data from UDE plus.
I don't know how I found
So I
on
just
the
want to send a
internet
link
these
to this,
slides. I was just like randomly
He's
Googling.
contacted me a couple of times,
Right.
asking, what was wrong with those experiments?
Like,
Or there's
yeah,
some kind of,
something in
in the syndrome data, there's sort of a peak.
Right.
Peak of
And you might have E plus,
yeah, I saw it. Yes.
and then he looked at our old data and he said, you don't rule it out,
yeah, go ahead.
which is probably true because there was that. But nobody seems to be interested.
I am, but
I am
very.
I am also interested. But you have no model.
We have a model. That model is not a problem. We'll always find a model.
What is the truth? That's it.
That is not a problem, but.
Yeah, always that's a mystery. Anyway, I like to measure relative to Muon. See. Can you do that in comment? Oh, yes. But then, as I say that, like no photon detection. Huh? No photon detection. No photon detection. What do you mean? In COMET, can you do the? In ordinary memory. Yeah. What could be observable?
So
That's
in
next time, maybe.
the end, the Peter experiment, I forgot the name.
Oh,
Milk out, right?
Yeah,
It was
yeah.
called milk out.
Milk out.
So they just,
They use the helium-3 or something.
Yeah.
no, hydrogen, they would capture and hydrogen. So what you actually do, it's like a PPC filled with hydrogen, right? And muon comes in and stops. Then you wait, you measure the lifetime. So now you stop the mu plus and you stop the mu minus. And you measure the difference with the effective lifetime because there is an ordinary capture rate that shortens the effective lifetime for the mu minus. This is the difference of 1 per 1,000 for hydrogen, but since they have like 6 orders of magnitude sensitivity for the lifetime, they just get this, right? So this is as simple and pleasant to see, yeah. As opposed to the liquid hydrogen where you have like all
P5
molecular issues.
Yeah, it's very.
And there is like a theory going in, and you trust it or not. It's just horrible.
The theory?
Oh, if you stop a mu minus in the hydrogen, right. So you instead you form a muonic hydrogen, but then this muonic hydrogen binds to another hydrogen, and then you have PP mu minus molecules. They have different arrangements of the spin. You need to know, and this different arrangement of the spin affect the capture rate. So you have to know which modifications of these molecules are in, and that is. It's not like it's not like what we saw yesterday. Dielectric susceptibility of helium-3. You cannot just calculate it like that, right? Yeah. It's like every atom will become a molecule, right? And you need to.
No. I mean the wave function of muon inside H2 is a problem.
No, but you need to know the spin orientation, right? Yeah.
Also, it's you don't know the.
You don't know. Yeah, you don't know the ratio of the.
Experimentally, I don't know. That's the
you only measure the rate, right? And you want to measure the rate, but it's different between there's 2 different modifications, right?
Okay.
It's. Right, so this. Yeah, but this radiative muon capture in hydrogen. In hydrogen, if you have lots of muons, you can do it. If you can do it in the gas, then it would be closing down that anomaly.
How many muons stop? Yes.
See, the capture rate is branching is for compared to the decay is 10⁻⁵, right? In hydrogen. But then the radiative rate is another 4 orders of magnitude down because you want I guess the more energetic end of the spectrum. So it's like digging out branchings of 10⁻⁷. It's not an easy measure.
Nothing compared to 10⁻17.
Yes.
We have a 10 to 11 million per second. So I would say that just one day is, we have many.
No, it's gotta be
But then also-
systematic error
Sure.
measurement.
Also,
obviously.
headache.
We are the master of these things.
Yeah.
What will happen for what's the next thing from Comet phase alpha becomes Comet phase beta or?
But nothing happened between now and in 2026. So 2026, we may have some very low intensity. But KK has some budget problems. So we have to start from very low intensity. And then I don't know how long does it take to make a phase 1 goal that we use after 2026. But from now to 2026, we're just working on and superconducting magnet. We will not have any beam there. So,
There's bound to be problems when you have beam that you haven't anticipated.
always.
Always.
Yes. And then simply just get involved. I hope that we can someday after 6. I don't know what is happening. Status. If you have any particular new idea, we can question. Yes. Zero new idea.
I hadn't been aware of the mu minus DEX stuff we talked about. That's very nice. Measuring the, I don't know.
Well, this is advantage, but then also about disadvantage also. So the reality is lots of different.
So you see more radiated muon, more things above the film.
I stopped sleeping for you. You stopped sleeping? Yeah, I didn't sleep today. I didn't sleep today. I wasn't sleeping. Really appreciate that. It's a sacrifice. I know. You have to listen to your thought. You noticed. I hope you know it. Completely by word. Hopefully. Does this work?
Next
week or so.
You'll get some message.
Yeah, it's always 5 p.m. But
I will be there. I mean, this conference stuff. As soon as they showed up, we go for dinner.
I see. You just struck up. Because I didn't know there was a fall. That's for your 30,000.
Awaiting. They're not quite there yet.
They're actually there.
They're on site, but not in that place.
Okay, then let's start the second session. So
The first speaker is Ken from here, University of Minnesota, and he's going to tell us about Mu2E. So please.
Okay, thank you. Thank you all for coming and enjoying our great weather. Sorry we couldn't have snow for you, but you know.
We'll take the record highest global market and all that. There it is. Come on.
Okay, I'm going to give a sort of picture tour. I mean, now everyone has heard a lot about U2E and COMET and knows the what's happening. So this is kind of a picture tour of what we're doing and where we're doing it and what state we're in right now. Minnesota is the state. Okay, so this is Fermi Labs for those who haven't visited. The high rise, the booster, and right over here is sort of the Muon campus right outside the booster. So here's the booster, here's the high rise 15, 16-story building. And this is G-2 sitting there, and this is the Mu2E experimental hall. So these things exist. Really, I don't have to stand up here and justify what we're doing this to this audience. And this is just another sort of cutaway version of what the Mu2E experiment will look like when installed. And you can see the snake-like structure, very much like COMET. We're all using the same idea. And this is where the detectors will be. And just for scale, these are people here. There's one there. There's a person there. And again, this is, it's a broad search for various types of theories that can be beyond the standard model, of which theorists are infinitely inventive. And what I like to liken this to is finding oil. And so what we're doing here is drilling test wells for the great pool of beyond the standard model. And we may hit oil. That is, we may find Mu2E, or we may eliminate some part of the geography so we can look more fruitfully somewhere else. And again, people have been talking about this, the idea of capturing a muon in an orbit around aluminum, which is what we will do, and look for an almost monoenergetic electron coming out. And this is with the exchange of a virtual photon to conserve momentum. And we're looking in a range that is very much higher than the standard model, which is unobservable. And so in that sense, we're very sensitive to beyond the standard model. And again, just as sort of this is what the experiment looks like. We're taking 8 GeV protons, smashing it on a target. Pions get produced and get reflected by sort of a magnetic mirror here, and then get fed through this labyrinth of magnetic field and collimators to come down here at sort of 50 MeV mu minuses that will then collide with our aluminum target. Some of them will stop. Most of them will go straight through, and everything will be spiraling in the solenoidal field, which is all the way from here to there. And we have a detector to measure the energy, a tracker in the magnetic field, and with a big hole in the middle to let everything we're not interested in go through. And so we're looking way over here. These are the electron, these are the muons, the regular muon decay in orbit. It's red, and it looks easy because we're way over there, but this thing has a very long tail. And if you blow up the tail to the level that we're interested in, it looks like it's screaming down here. And we're looking for a signal there. And the signal that's shown here is 10 to the minus 15th. So 1 to 2 orders of magnitude above what we actually expect. So we do worry about getting buried by this tail, which is sensitive to all kinds of things, including what's in the way in the experiment. You've seen this before. This is the trick of we're delaying the sensitivity, which is of the experiment to after lots of things pass through. On the other hand, here's our simulation of what happens during the live time in our detector. So there's still a lot of stuff coming through, coming from the target and spiraling around and bouncing, even bouncing back and forth, rescattering off the collimator or the calorimeter, which is back here. So that's why we have a segmented tracker that we can handle these rates and we can handle this radiation. And the tracker is basically built like this out of segments of a third of a circle. And there are many of these at different angles going through. And in the middle here is where almost all of this stuff is going. And this will be the decay in orbit, which is the main muon signal, which is like this, which will not rack up there, but this is what we're looking for, is sort of a big circle that comes and we see it. Okay, so this is just to give an idea. There's this muon beam has a long journey where the beam starts really at the LINAC at Fermilab and then through many rings to the muon area. This is the G-2 experiment. And unfortunately, we can't run at the same time that G-2 runs, or vice versa. They can't run when we run. And so this is where we are now. And these beam tests, we're putting the beam in, and it's kind of 90% installed. But of course, as you know, with a beam line, it's either 100% installed or it's not installed. But the stuff is there and it's being tested sort of parasitically. Okay, so here's the guts of the U to E experiment. Again, this is our what things look like, a person scale. So it's not huge, but big enough. And we have basically 3 kinds of solenoids. And these are all superconducting solenoids with all the agony attached to superconducting solenoids. We have a large aperture solenoids that will wrap around the production target with a tapered field. And these things are almost delivered. That is, you know, the solenoids are in the mail, but they've been in the mail for a while. And they're being made by General Atomics. The transport solenoids, that's these guys, are at Fermilab and are about to be shipped to the experimental hall. I'm not sure if they made it or not recently, but are on their way to be installed. And then the largest solenoids are also being made by General Atomics, which are for the detector region here. And they're not quite, the last coils are not quite finished yet. So we expect delivery in the summer of 2024, which is almost upon us. And the next, so the other thing is that as an experimenter, everything about this experiment is impossible. Okay. This is pushing the limits on everything that we know how to do. And the targets are no exception. We have the tungsten production target, which is which has been designed and exists. And we have the aluminum target, the stopping target here, which is also designed and exists. And it's made up of these very thin aluminum foils with a hole in the middle for things to just keep going through. This is the tracker, which we've been dealing with mostly here in Minnesota, building the pieces of it. It's made up of straws, which have been mentioned before. So these little guys, they actually are like soda straws, and they're made by a soda straw company who actually wound them, but out of material specified by us and tested by us. And these things are very thin. They have a wall thickness of the size of an average human cell. And so they are fairly delicate, and they are the same design, same parts in their manufacturing as G-2 straws. And you heard before, G-2 straws are leaking after some time. And so these straws were made a little bit differently than the G-2 straws. So we're hoping we learn things from G-2 and they'll be okay, but they're undergoing a lot of testing. In any case, there are 96 straws in one of these modules. There's 6 modules to a plane. There are 2 planes in a station. We put together the stations in this frame, and voila, the tracker. And this tracker is about the size of a U-Haul van. You can see people here working on the module. Inside the modules are all the electronics, which has, of course, been a problem because of supply chain. We're just now barely getting the electronics that needs to be installed, but all of the modules exist and have been shipped to Fermilab and are undergoing testing. This is a picture with some of our Minnesota people who are resident at Fermilab now, looking down the hole, and these are undergoing long-term leak testing. So when we find things that happen, they get investigated and fixed. And this is just some pictures of how these things were made in the Pan building, which is right over there by undergraduates. There and there. And this is, again, some of the Minnesota and ex-Minnesota people at Fermilab working on a plane at Fermilab. So this all exists, and we expect to have this tracker installed in 2025. Downstream of the tracker is a calorimeter, 2-part calorimeter, which is here, which is cesium crystals, which gives us a fast signal and identification of an electron. And that is also almost completed, should be completed in 2024. And one segment is pretty much completed, and the other is being built and installed. But yeah. Then there's the cosmic ray veto, which you heard.
Question?
Yeah.
Calorimeter, you say 10% resolution. Is that RMS or sigma? And what's limiting that resolution?
I don't know. So I'll defer. Bertrand, do you know? What is it, RMS or sigma, the resolution?
You're asking me?
No.
Sigma, I think.
Yeah.
Sigma.
It's
Okay.
covered by the length of the crystal. We just don't have enough
Not
radiation.
entirely.
What's the energy?
What's it? 100 MeV.
Yeah,
So it's 100
5
MeV plus or
MeV.
minus 10%.
But the energy of the electron is determined by the tracker.
Well, so I mean, it's a bit more complicated. If you look at the spectrum, there is the tail because of the leakage, and so you do an equivalent of the thing we have max. Get the one resolution. I can show you the plots. To explain that, but it gives a rough order of magnitude of what you expect with that gallery.
Okay, the other piece is the cosmic ray background shield. It's not really a shield. It's a veto. The whole experiment is covered by scintillator. The scintillator modules. Are co-extruded scintillating strips with a wavelength shifting readout, very similar to what's been used in neutrino experiments. And again, here's the coverage. This is a person. It's most of this is now completed and is there at Fermilab. But there's a lot of things being tested and final electronics is being built. The electronics is some of the slowest parts in the experiment from supply chain. And there are many other pieces to this. I haven't talked about the beamline, the extinction monitor. There is just a lot of pieces. This is our schedule right now. So we need to get our first run in before there's a long shutdown for the Dune beamline being put in, which will turn us off. And then we come back after that. And so we expect here to get a run of some number of months, depending on how long it takes us to commission the detector. So we're hoping for maybe 6 months of running, depending on how optimistic people are. And before that, the detector, the calorimeter and the tracker will be removed, will be outside of the solenoids. So pulled out here as a train for commissioning and testing with cosmic rays. And so we'll do all that first before we put it into the solenoids. And hopefully data taking begins in 2026. More than hopefully, sure better. And, again, this is kind of where we are. The accelerator and proton beam modifications are in progress, but 90% done. Production and stopping target are complete. Muon beam solenoids will be complete soon. Detector solenoids in mid-2024, which it's almost 2024 now, so also soon. The tracker modules are complete. The planes are 75% assembled, and the stations will get assembled when the electronics is here, and the electronics is being delivered now. So that's starting. The first half of the calorimeter is complete, and the cosmic ray veto is 98% complete with the electronics being assembled. So we think we're in good shape to start taking data on schedule. And the next step is MUTE-E2, but we're thinking about it, and everything that's difficult about MUTE-E is more difficult about MUTE-E2. For instance, if you build it out of straws with the same technology, the wall thickness has to be half what it is now. which means the straws right now are very delicate objects. And they will even be more delicate. But hopefully we have some time to think about this to run. But everybody is welcome to join in if you wish on this, in this even more challenging experiment. And this is the collaboration. We have over 200 people, 38 institutions from around the world. And everybody's working very hard to get this thing up and going. Thank you.
Thank you. So time for questions.
Well, thank you very much. Very nice talk. Can I ask what is sort of a single rate of a cosmic ray veto system?
Sorry, what's the
Single rate, detector rate
the single detector rate?
by, say, like neutrons in the background.
I actually don't know that. Some of that will be will depend on the environment of the accelerator.
Yes, yes.
And I think that's. Bob, do you have?
I don't remember the number. I
Yeah.
don't want to say the wrong number, so I'm looking it up and I'll.
Yeah, okay. But on paper, it's fine, and we're worried about it. And so I think this was part of the discussion that you and Bob had before about, yes, you can test the cosmic ray veto on just cosmic rays, but we worry about the environmental beam miasma of the accelerator. That we won't be able to test until we turn the beam on, but we will.
I think that's very important that make sort of accidental veto of the signal.
Mhm.
I can, nice talk, nice pictures. Quick question, how do you, what's the readout scheme? Do you have a trigger, which is based on the crystals, or how do you decide to read out an event in this?
Well, you know,
At such a high rate.
a trigger is in the eyes of the beholder. And I mean, we don't trigger the way we used to trigger. That is, it's just it's an electronic gate.
Based on the beam,
Beam
just on the
pulse,
beam
yeah,
pulse. So
yeah.
it's a continuous readout.
Yeah, it's
Everything goes to everything goes to memory, and then so it's a
Yeah.
okay. So there's no pre-selection, no.
no,
And how many?
there is tagging, but that's
Sure. How many straw tubes does a bona fide electron pass through as part of your track?
let's
You
see.
get about 20 hits.
20 hits.
Yeah.
Yeah,
So that's a pretty substantial number. Okay.
yeah, you get a good track on these things.
Right.
So
Well, the logic is you find the signal in the cesium iodide, then you track it back. You look backwards and through the.
that's not necessarily true.
All of it.
Yeah, so we have two schemes. One is exactly what you just said, and the other one is going the other way.
Mhm.
Okay,
And then we have one which is a joint,
okay.
right? And so everybody will have their favorite. And then, everybody will be blinded and we'll all argue about it. And that will be the fun part of
And
it.
you never publish because you never agree, right?
But that will be the fun part, right?
But in fact, I mean, with simulations, at least, we can find the tracks in the tracker without any starting point, say, from the calorimeter.
Okay, but the unambiguous signal is a track in the spiraling appropriately inside the silicon, inside the strip.
Inside the
The
straws.
straw tube, sorry, too many
Yeah.
technology, inside the straw. That is your signature. That is the thing that says we have seen the right energy event.
Yeah, and the calorimeter, checks E over P, like every fixed target experiment in the world. Right, it does particle ID, really does a good job at separating muons. We get these weirdo events that go down the solenoid, turn around and come back, right?
Mhm.
Or we get ones that are coming upstream and turn around and come back because of the magnetic mirror. And the calorimeter is very good at helping us with those. So it plays, even though we've been sort of dinging on the energy resolution, but it does all these useful things that a tracker can do.
Okay, oh, nice. Nice concept.
Any more questions? Don't see any more, so let's thank Ken again. Okay, so let's start the second talk. The talk is by Bertrand, and he's going to tell us about the future program of Muon charge Lepton flavor violations. Please.
Okay, so I realize I take some risk of discussing the future of this program just before the P5 report. Hopefully they will have the good taste of agreeing with me. I should also say that, Bob, Kuno-san and Ken already said a lot about what I'm gonna show you. So I will issue a blanket as they said before, and we will go over some of the material and why does it need to work? And nope, I'm trying, but is this one? Okay. Okay. Oh, sorry, I got almost. So I think we already all know that CLFV, if you observe something, it's a clear indication of new physics, and you need multiple measurements to try to understand the underlying physics. What I think we haven't discussed so much so far is the connection between CLFV and neutrino. It turns out that there are many mechanisms to generate a neutrino mass, and most of them induce sizable CLFV rates, which can be used, of course, to differentiate the models. And I think, given that the strong role neutrino physics is going to play in the US in the coming years, it might be a good idea to try to discuss and emphasize a little bit more this connection between the two fields. I'm also going to discuss mostly muons in this talk. So we have all seen previously the three main muon modes that they probe mass scale already at a level of 1,000-ish of TeV, and that the complementary is really key. Once again, this slide shows you that if you look at the d dependence of mu-to-e conversion as a function of z, as a function of the, on the target material here, you see that you can learn something about the nature of new physics, especially if we have white no measuring aluminum. If you really want to try to go to IZ material, that's where it's most easier to do. So coming back to these plots, just showing them back and discussing those plots we have discussed before. We did some work with Sasha. To be honest, Sasha did 95% of the work, and I did some of the plots and other things. And I wouldn't dare to explain EFT to Maxime here, but I'm going to try to give you the idea of what we did. And so this work starts with the following effective Lagrangian, which has the experimental mass scale and muon mass, basically describe the three muon modes I talked to you about before. You get a dipole term and then contact terms for mu-to-3e, decays, both scalar and vector contributions, and a contact term for mu-to-e conversion. And here we make a small approximation that all the light targets are basically the same and all the AV targets are basically the same. The goal is really to try to be able to plot constraint in the smallest dimensional space, to try to have too many parameters to explore and scan. And so we make a few of those approximations to help us. And for the sake of concreteness, we basically take aluminum for the light and gold for the AV ones. So as you can see, in this AFT picture, there are many operators, but only a few measurements. And here the idea was to take a fairly judicious choice of basis vector. And if you make a few more small approximations, you can find basically a four-dimensional subspace, which corresponds in good approximation to the weights you measure in the lab. And that was the idea. And so you parameterize this subspace with spherical coordinates. And then you obtain constraint at the Newton scale by running RGE's equations. The way I asked Sasha, she basically told me she put that in the computer and you get the answer. So that's my understanding of theory, which seems to be much easier than experimental physics. So I should have done that. One point, we make this approximation about light and heavy. Axton has done, tremendously great amount of work to understand better the effect of the nuclear structure. And so I invite you to look at this paper to understand more on that. So if you do that, let me first discuss that box and then the plot. So you can parameterize this four-dimensional subspace with four angles. It has D, V, S, and phi. Theta D basically gives you parameterization of the angle between the dipole and contact terms. So if theta is 0, it's all dipole. Pi over 2 is all four fermion terms. Theta V is the angle between four fermion operator on leptons or quark. So we can have either only leptons, only quarks, or in between. Theta S is the angle between the scalar and vector operators for mu to 3e. And finally, phi is the angle between light and heavy operators on mu to e conversion. So you can pick different point parameter space. What we did for those plots, then we introduced this variable kappa d, which is basically a smart parameterization of that theta d from De Gouveia adapted from him. What it does, it basically blows up the scale at large, at theta d close to 0, or pi over 2, that's where you have essentially either dipole or either a contact term. And that's what you have on those plots. So when kappa d is very small, it's basically dipole dominated. When kappa d is very large, it's contact dominated. And in between, you have a mix of the two. And that dip here is because that's where as for you, Chris, the dip is where the dipole term cancels the contact terms. So that just happens there. And so for those plots, we basically took representative values of theta S, theta V, and phi, basically kind of in between all of them. And that's what you see for the current situation. We have constraint on the level of roughly 1,000 of PV. And so the real great progress on those plots is that now you can plot the three, the constraint for the three type of decays you get, and not only two that we had before. And that's the soon-ish near future. I don't know exactly when it's going to happen, but that's COMET mu2e, MEG2, and mu3e. And you see already a nice improvement on the range. What we were thinking is, okay, what do we need to do to go way beyond that? And that's what is future question mark picture is when you will get an AMF as prism style where you would improve, by, maybe 1 to 3 orders of magnitude about COMET mu2e, and that's mu2e to another order of magnitude here. And we also put, as a guideline, what you would get with mu2e gamma at the level of 10 to minus 15. And I don't have a good number for mu3e, so I left that there. But that shows you basically the qualitative feature is that if you have mu2e conversion can really increase the scale, and then you really need to have mu2e gamma at a much higher sensitivity and as mu3e as well to basically catch up with that. You also see that if you're unlucky enough to be right there in the dip, that's the same plot as a function of phi. So if the gold, you were in the dip for aluminum, if you switch to gold, you would certainly see something, and the same if gold is basically at 0, aluminum would see something. So that's the importance of measuring several targets. You never know where you might end up.
What is the dip due to?
The dip is what I said before. It's basically when the contact terms here cancel the dipole term. And that depends on the type of nucleus you have. In this simplified model, you get light or heavy. So depending, if you are either if that's a heavy part that cancels the dipole, then you are good with the light, and vice versa. That's the idea. But the bottom line is that if you really increase the sensitivity on mu2e conversion, then you might also want to do something about the decay experiments to match that up. So let me just briefly discuss current and next generation initiatives and see where our the limitation factors. So we have already seen mu2e gamma and mu3e with ear talks later this afternoon about those experiments. Bob discussed the limitation. It's basically in the case of mu2e gamma, for example, the limitation is really then arising from accidental backgrounds, and you see it scales as that formula. The contribution for the photon is basically much larger than the other terms, and so you really want to work on improving the detection and the resolution in the photon to improve your sensitivity. And as he said, there are two ways of doing that. I will come back to that next slide. And obviously, if you want to improve your sensitivity, you're also going to need more muons. And so those two possible options that have been studied so far is either the calorimetry route, where you really improve your calorimetric measurement, or the photon conversion route, where you basically have a converter, either active or passive. You convert your photon, you get much better resolution on the photon, but obviously lower efficiency. And so that plots data a little bit, but I think it's going to show the qualitative features. It's basically with some assumptions, you see what's the ultimate reach of those type of experiment. That's make 2 the blue one. The calorimetry is the dark red-ish here. And the conversion, depending on the assumptions you make for the type of converter and how many converters efficiency, at those curves here. And the bottom line, you see that they basically all flatten out and plateau around 10 to minus 15. And so if you really want to take full advantage of having 10 to the 10 mUs per second or more, and break that 10 to minus 15 floor, I think you really need a novel experimental concept that's even going even beyond those, calorimetry or photon conversion. And we think the whole thing to really drill down. One very interesting question, and I think that's a very challenging question, is to see if you were to do an experiment with a converter, you see that you basically have 3 electrons, positrons together, which really looks like mu2e. So can you find a very clever way to build a single experiment that would search for mu2e gamma and mu2e at the same time? We spent quite a few hours on that question, and we didn't find an answer, but maybe someone one day has a very good idea. The muon conversion, we just got 2 talks on COMET and mu2e, so I'm going to skip that. We saw that the main limiting factors are this beam flash, all those particles arriving just after the photons hit the target, which means that you need to wait until that flash subsides. And so you cannot measure conversion in IZ material because they have a very short muon atomic lifetime. And obviously, you also need to have very, very well-defined pulse beam, very good extension. If you start adding protons in between, right in the middle, that's obviously going to spoil your measurement. And then if you want to do better, obviously, you need more muons and a better detector. So there are several proposals for next generation. We just saw mu2e2, which is basically an evolution of mu2e, trying to improve on several fronts, the detector, the more beam. I'll skip that. We discuss that. And a few words about muonium and tmuonium. We haven't discussed very much about that. So you all know it's a pure QD state. The transition, which are delta L equal 2 process, extremely suppressed, but could be enhanced by new physics. And I was at this CLFV conference organized by Bob earlier this year. And Dev showed a model, a leptophilic 2-HDM model, in which basically muonium provides the leading muonium and tmuonium transition, provide the leading constraint on this type of model. And I think that's the first model I saw where muonium and tmuonium were the most sensitive constraints. So that I thought it was worth showing you that as well. And so the best limit comes from the Max experiment, which was the previous millennium, should I say, based on a fairly, by today's standard, a fairly small number of muonium atoms, a few 10 to the 10. And so the idea, you shoot your mu plus beam, surface mu plus beam into a target. Here it was a silica powder target. You form your muonium, you transition, and then you detect the hard electron from the mu minus decay this time.
and the soft shell positron is reaccelerated and annihilates in a target where it's going to produce 2 photons, which are going to be detected by a calorimeter here. And so you use this triple coincidence plus cuts, angular cuts on those pair, energy cuts on those pair, and energy cuts on that electron to basically find your signal. So you didn't find anything and set some limits on this transition probability. The bottom line is that technology has evolved since, and people think they can do much better. And someone found this very clever acronym called MACE for a new experiment that's going to smash this previous experiment and do hopefully 100 times better with basically the same idea. The proposal, I haven't followed that very closely, but last time I looked at it, the proposal was to do this experiment as this new Muons facility in China. They expect a muon beam with a fairly large, fairly high brightness. And the concept is basically exactly what I already discussed, except they do much better on the technology. They have a better target to improve the muonium formation rates and a few other things. And so I think there are ongoing physics studies and detector R&D to make a proposal for that type of experiments. Perfect. So what I really want to tell you about is next generation. So what can we do after that? And that's what Bob alluded to, what we discuss. And it's still very conceptual because that's really high-level discussions. But we have been brainstorming a little bit about what we call this advanced muon facility, AMF, which is a proposal basically for a new muon complex for the next generation of experiments. We have been mostly thinking about it for Fermilab, but that could also be done at JPark. And so the idea is really that this complex would provide the world's most instant positive and negative muon beam to enable a whole suite of muon experiments, not only muon conversion, but you could imagine decade and transition experiments, muonium anti-muonium oscillation, muon spin rotation, and I don't know what else. We haven't had that much time to really think about all we could do. And so the goal of this facility would be ideally to provide a beam that has the lowest momentum and small momentum bite, so that you can really stop all those muons in a very thin target, which is really helpful, and we'll see why. A very pure muon beam to reduce all the backgrounds and help you realize condition experiments in IC targets. And either pulse or continuous muon beams. You like pulse beam for conversion experiments, and I will explain you why in a minute. And you like continuous muon beams for decay experiments, as we saw before. Let me just go back to that slide. As we saw before, the accidental background scales with the instantaneous rate. So if you can spread your beam over a long time, is much better than having a short beam pulsed, because then your accidental background goes up by quite a lot. And that concept, this facility could be achieved with basically a small muon storage ring, and Kuno can explain us why, based on this fixed field alternating gradient synchrotron with phase rotation with this prism concept. We also discussed the possibility of having a very bright surface muon beam, which could provide a low momentum monochromatic beam for positive muons. But we really want to study the FFA because that might work for both charges, and so you get 2 for the price of 1. And so let me just rephrase what Kuno-san discussed about the prism concept. And so the idea is to have a very intense megawatt photon beam with very short pulses, so ideally 10 nanoseconds or less. That is going to hit a target in a capture solenoid to produce pions that will decay into muons. And then you just collect as many muons you can. You inject them into this fixed field alternating gradient accelerator, this ring. And what this ring is going to do is phase rotate the beam, trading energy for time. So essentially, you accelerate the trailing muons that have less energy. You slow down the fast ones. And so you get, you rotate that beam, and you get at the end of thanks to radio frequency, and at the end of the rotation, you get a very small energy spread, but your beam then is spread over time. And you can extract that. What it also buys you is that during, it takes a few turns of the ring to achieve this phase rotation. And during those few turns, your pions basically decay. And so your pion contamination now has really reduced. And you end up with a very pure, monochromatic, hopefully low energy muon beam that you can extract to your experiment. So that's the goal. To do that, you need a very compressed proton bunch, because if you want to trade energy with time, if your delta T in time is large, then your delta E is going to be large at the end of the day. So you need a very short pulse, and obviously high power beam to achieve high muon rates. And the more power, the more muons. Just a few words about the FFA. So it's not completely up in the air. As Kuno said before, there has been a proof of concept a couple of years ago showing that this could work. And that's essentially what we have as a concept for AMF. So you get a proton driver with a compressed compressor to compress, bunch those protons and make short bunches. The target, the front-end target, and then this FFA to create a pure muon beam, and then the experiment you would extract. I've been instructed, Chris here. Any resemblance with graphics from the Muon collider is purely accidental. I was told by my legal team to tell you that. And then we have been thinking a little bit about concept for this FFA. Could be circular, racetrack, geometries, scaling, non-scaling options. Even if you could do mu plus and mu minus at the same time, so it's all in the work. There are obviously strong synergies with the Muon collider, especially for the front end. Sorry, I keep pushing the wrong button. For the front end here, the target, it's a major challenge. I mean, the megawatt target in the solenoid, the same challenge faced by the Muon collider. So obviously, a lot of synergies on that front. And so that's a bit more recent conceptual design for this type of machine facility. You get your proton beam hitting your target in your capture solenoid. You transport your pions and muons via transfer line to this FFA, which shows here a racetrack geometry. And after a few turns, you're going to extract those muons and transport them to your experiments. So what does that buy you? As I said, there is already no beam-induced background. Your pions decay in the FFA. Your beam flash is also taken care of. You don't have antiprotons, other delayed electrons or muon decay in flight, which means that first you can measure short muonics for atom lifetime. So you are in IZ material. You also ease requirement on out-of-time protons because you have more ways to basically get rid of those. And since you don't have all that flash, you also have way less radiation in your detector. All good things. The very cold beam means you can stop your muons in a much thinner target. Ideally, if you have just a single foil to stop them all would be great. And so you reduce energy fluctuations in the material when you, for muon conversion, for example, the recording electron is going to see less material, so way less energy loss fluctuations. It's going to improve your momentum resolution, and you're going to be better at rejecting this what we call DIO background. There's also a fairly low duty cycle, much lower than the current scheme. So the cosmic induced background is going to be just lower because you spend less time having detector looking for signal. A few words about compressoring and all that might play out at Fermilab. So PIP2 is obviously a good candidate to use a good candidate accelerator to provide the megawatt beam we would need for AMF.
The only issue is that it's basically a continuous beam, which is, as I told you, not ideal for this type of machine. So you need a compressor ring to rebunch the beam and to provide those short pulses. Few possibilities have been looked at. It's still not very conceptual. Either a compressor ring, you might be aware of this ACE program at FNAL, this accelerator complex evolution, trying to upgrade the accelerator, and in that there are different type of scenarios. They are all outlined in this document, but in all those scenarios, you could imagine a 2GV ring that would serve as a compressor ring for this type of facility. So it's also in discussion, and we're interacting with those guys to understand what we could do. As you can imagine, there are many challenges to be solved to build such a facility, ranging from the FFA ring design to the target and capture system. This one is really challenging. You want a megawatt class target in a solenoid. I don't think anyone knows how to do that, but as I said, it's really in full synergy with the neutrino factory and the Muon collider. And then you need also to design the transport lines into and outside out of the FFA ring. Out is fairly easy, in is much more challenging because you have very different beam dynamics coming in and to the FFA. The compressor ring is also something that's not easy to do, but might be doable. And that's a potential timeline we outlined during the SNOMAS process. So you see how that might play out. And if we are really aggressive, the goal would be to try to design a concept for AMF and at least flesh out designs for some of the experiments you could do there by the end of this decade. And then we can, as I don't remember who said that the other day, dreaming is free, so maybe then we could construct this facility and start taking data fairly soon. I'm almost done. So we plan to form a team to address those challenges and develop this concept, as I said. And if you have new ideas for exploiting the physics potential of such a facility, you are very welcome to come and talk to us, because the more the merrier. So instead of a very long conclusion, let me just say that the future is bright. I think this AMF facility really works. And please get in touch if you are interested or if you have good ideas of what we could do. And that's it.
Thank you. So questions or new ideas?
We have 5 minutes before the movie starts, so.
Just a super naive question. At some point, if you march down in the branching ratio, you will get some irreducible backgrounds like neutrinos interacting in the wall, making electron out of the charge currents and so on. Is this ever a concern?
I would be very happy the day it becomes a concern. I'll put it that way. I'm looking forward for that, yeah. I think we have still some margin before getting there.
I have a documentation question. So do we have a definitive document that gives us the different models that we have in MUTE and their Lagrangian densities and the calculations of branching ratios, constants, mass scales, and all of that? Is there anything in DocDB that we can just look at that has all of those?
I'm not sure. Maybe you should discuss, because I'm not sure what you're referring to. I mean, that all depends, you know.
For example, the leptoquarks, if I wanted to see the different terms in the Lagrangian.
So I don't think I ever seen a compendium of models and references. I have some scattered here and there. I don't think we made an effort to really collect everything in a single place. That might be a good idea. So we have that facilitate references, but yeah, there are a few. Usually I go to a few reviews and then there are references in the reviews, but we might want to do something along those lines, yeah.
Thank you. Just one more question. So when you mentioned that increasing the Z number will effectively make things better for us in the future, right? You also mentioned, I think it was in Bob's talk as well, that the time scale would be shifted a little bit. So what is the reason that we went for aluminium instead of, for example, something of a higher Z?
Okay, so let me get back. I think Bob already explained that, but so in the current scheme, in the Lobachev's scheme, we have the D2E scheme, and just taking 1 minute here. Yeah, this one, okay, this type of scheme. I had that plot here. So when the protons in the primary target to produce your pions that decay into muons, they also produce slew of other particles that are going down the transport beamline into the detector. And so basically this whole region here is swamped by backgrounds from either of those primaries coming down, and then you get pions also coming down that can decay, that can produce some background. So if you want to get background free, you need to basically wait something around 700-ish nanoseconds. We can discuss more or less a little bit for all that thing to die down. And then you can do your measurement. Now, if you look at the muon atomic muon lifetime, you see that for aluminum, you're still at something where you are basically 874 nanoseconds. So if that's 800 nanoseconds, you form your the muons get captured over here. You can wait another 700 nanoseconds, and your muon's still gonna be there. If you have much shorter atomic at higher Z, you have a much shorter atomic lifetime, which means that those guys, if they form here, basically get captured right away. And so you can't wait that long because you have no more muons at that moment. So this Lobachev scheme basically dictates the type of target you can use, because they need to have a lifetime, the muon needs to have a lifetime long enough where you can wait with good efficiency. And so if you go to this other scheme, this AMF, FFA scheme, then when the muon beam's coming out, you don't need to wait because you don't have all these backgrounds coming with the muons. And so then you can afford to just look at the signal right away, which means then you can just look at those IZ target materials.
Thank you.
That's the trick.
Hitoshi's putting up his first slide now.
Yes.
Just
Okay.
general interest.
Let's. I think
maybe
quick one.
So in a compressor ring, you said that the 10 nanosecond impulse width, can you make it even shorter? Because it's affected the phase rotation performance.
Yes. So we looked at the first people who looked at the compressor ring. They think that 10 nanoseconds is already fairly challenging. So we really need to go back to that design and see if we could do shorter. But yeah, that's tricky. That's difficult.
Along the same lines, if you can you raise the energy of the compressor ring to 3 GeV or higher, so you can produce kaons, and then to make it useful for kaon physics, you would have to get to 100 picosecond bursts.
Yeah, what we, in the context of snow mass, what we thought about was, taking PIP2 and plugging PIP2 into a compressor ring and try to keep it cheap. And so it was 800 MeV, which is as far as the compressor ring, it doesn't like that much. If you get something at 2 or 3 GeV, the compressor ring is much easier because space charge effects go down with energy, and so it makes your life easier. The problem is that you need to build something, outside the compressor ring to bring your protons from 800 MeV to 2 or 3 GeV, and that's expensive. So if this ACE program indeed moves forward, we're discussing options to have a 2 GeV spigot, maybe a 3 GeV spigot. That depends exactly on what's wanted. That could do some of that physics too, yeah. But it's really, right now, it's really everything is really up in the air and up for grabs. So we just made a concept that seems to be, the cheapest we could do. And there might be ways to have more synergies, might be a bit more expensive, but yes, we're looking into that.
Okay, then let's thank Bertrand again. So we will show the P5 here. And then is the lunch box outside?
There should be lunch.
There should be lunch box and probably
For those who.
Yeah.
So there's apparently a problem. I don't know if you can get in because the webinar is exceeded 500 people, but I'm in and you can file out. I anticipated this.
Reserve.
Yeah, no, I locked in a half an hour.
Is there anything that they do?
At the whole.
I read the whole
Actually,
chain.
Teresa Nightingale.
Right.
I think that proves that this is just ill thought out, misguided action policy in this office.
Okay. Oh, no, we got a lot
There's something I can. This thing that's never been a problem before, and never raised a concern. Stop making problems that don't exist. We're not wrong with this bureaucracy we have.
You know what it is.
They found some sentence maybe in our contract, maybe.
Right. Trust your colleague not to be on the case, right?
Right.
You're not gonna make money out of it.
Right. Exactly. I'm not trying to live there for free and save
Right,
bucks.
right.
Yeah.
Let's say if you want to do heavy lazy, yes, then maybe you should.
No, I do a lower rate run.
On the mind of the community.
All
All of this, of course, was complemented by talks and information about the international program. As I mentioned, particle physics is an international global enterprise, and it's important for us to take that into consideration. Over the summer months, we also had a couple of virtual town halls to give people additional chance of engagement. And I just wanted to point out there that we also had an exclusive session for early career members. And this was really critical. This, the snowmass process that led up to this P5 as well as this P5. We heard during this process voices of the early career members. It's clear they have a stake, an important stake in this process. It is their future that we are discussing here. And we wanted to understand their concerns and considerations. And so hopefully the plan that we will present today will speak also to our early career colleagues in the field. I should just mention that for all of the town halls, the organization offered live captioning and ASL, and we also ran some surveys, and it was found that this was actually quite valuable. And we hope that this will be something that the community will continue to provide to make our meetings more accessible for everyone. The community engagement and information gathering phase continued throughout the year. We had talks at the DPF session of the April meeting, at the Korea networking workshop in the summer. We listened to the science workshop, CPC workshop, at all of these major meetings of the community. There was P5 representation, both in terms of providing updates on where the process is, but as well as listening and really hearing what are the issues. And regular updates were sent through the Snowmass mailing list, and we worked with DPF leadership to make sure that the DPF community is informed about the status of the process. And we have, over the last few weeks, updated usparticlephysics.org, and this will be a place, or is a place as of right now, 1 o'clock, where the report and materials will be available for download. And this is also the central site where we plan to make materials available for all of our rollout activities. Following the information gathering phase, we went into a series of meetings that really were the deliberation phase. We had a number of in-person closed meetings over the summer, several days each. Again, we moved around the country to make it possible for everyone to participate as much as possible in person. And these in-person meetings were invaluable in really talking to each other and discussing the issues and the projects at hand.
Between the meetings and for the rest of the year, we also had working groups and weekly and sometimes several times a week Zoom meetings. And they helped us, with all our considerations. I wanted to acknowledge the additional input that we got from many of you, not just the scientific community. It was also very important for us to have interactions with the agencies, and we're grateful for the interactions we had with Dr. Burhe and Dr. Kang, as well as many program managers, staffers, officers from DOE and NSF. It was important for us to understand the boundary conditions, the constraints that we are dealing with as part of this strategic plan. As I mentioned, international perspective is important, and with input from people from the government and discussions, in particular Cole Donovan, we appreciated the complexity of what it takes to launch international projects and actually make them succeed. I also wanted to acknowledge the community input that we got beyond SNOMAS, and that is from the International Benchmarking Panel, the Computing Frontier. DPF leadership was extremely supportive in working with us, and of course, input from our previous P5 chairs, Steve Ritz, and previous HEPAP chair, Andy Langford. And we also received input from the Committee of Visitor report chairs. Following this, we went into a writing phase, which became quite intense. We interacted a couple of times with the agencies. We gave them briefings of the preliminary recommendations. And then towards the fall, we ended up writing and working on the layout of the report and on the presentation that some of you on the HEPAP committee now have in front of you. I wanted to point out that we continued what was done also in the previous P5 process. We had a peer review, a confidential peer review of an initial draft of the report, and we are thankful for the feedback that we received, many important comments. I should point out that during this peer review process, we did not change any recommendations. The input that we received was helpful for us to understand what we could clarify, how we could present things better, but it did not in any substantial way change what we are recommending in this strategic plan. And now this gets us to today, where we are here at the HEPAP meeting, presenting the final report for your consideration and discussion, as well as the HEPAP vote tomorrow. If HEPAP accepts it, then we will work with DPF on the rollout, and we have a number of events planned, including a town hall, to discuss this plan further with the community in the coming days. To give you a sense of the challenge that we were up to, I wanted to just show you a couple of slides that indicate the challenge with budget scenarios. As you heard in the chart, we were given essentially two budget scenarios. One that was based on initial increase from CHIPS Act plus 3% increase over the years, and the other one that is less favorable, which is 2% increase. And of course, if you fold in inflation, it comes out to be an actual decline. So if we take roughly 30% of the total HEP budget here as something that we can allocate to projects and deal with, then these are essentially the two budget curves, budget scenarios that we would be looking at in P5. And this is just a toy graph to just give you an appreciation of the prioritization that we had to go through. If you overlay now the ongoing existing project, this is how it looks like. So basically, you already see that in the coming years, the existing projects that are currently underway, under construction, are essentially saturating the budget scenarios, and especially in the less favorable one, you're already seeing some challenges. And then if you add on it the ambitions, ideas, and vision of the community, you see that, it becomes a challenging problem. This, of course, reflects the input that we received from SNOMAS, the many ideas, it's reflection of the creativity. And I should point out here that this, of course, is projects only. We don't have budget scenarios for the NSF, and it does not include an onshore PICS factory. So understanding the cost timeline of the projects is critically important to developing a robust strategic plan. And so we decided early on to form a subcommittee on cost, risk, and schedule as part of P5. It became clear to us that understanding the maturity of cost estimates, the risks, the schedule is important for us so that we can develop confidence that we can stay within the allocated budget scenarios. The lesson from the previous years, of course, is that sometimes cost of projects can increase by a factor of pi or so. So we drew on the expertise of some of the experts in the community. A subcommittee was formed, and J. Marx agreed to chair it. The subcommittee involved project experts from all of the major national labs, and we are grateful for the labs and to their leadership to make these people available, and of course to them for investing the time and the effort. So we had colleagues from Berkeley Lab, Fermi Lab, SLAC, Brookhaven, JLab, and Argonne help us understand the cost and risks and schedule of the projects under consideration. The charge that we gave to the subcommittee was as followed, and I just wanted to go through this briefly so you understand what this subcommittee, what information they generated for us and what they didn't do. So the idea was to get information from them about the high cost projects, everything above 250 million in FY23 dollars. And it was clear, given the time pressure, the schedule, that the subcommittee could not prepare its own cost estimates. They assessed and evaluated based on what the proponents provided. They received additional questions. The committee provided expert evaluation of these, and also looking at the overall situation of these projects. And we also asked the committee to comment on operations costs, doing commissioning, just to get a sense of what is coming down in the out years and what we have to account for. The committee provided P5 with a confidential report, and they provided us with their expert opinion on the uncertainty ranges for projects. So basically, we learned what would be a low, medium, and high estimate for various projects, and how these projects might evolve over time. And that gave us the information to then look at it and see how it fits into the different budget scenarios. So with this information in hand, we started the deliberation process, and I just wanted to say a couple of words about this. When we started this, it was clear that everything had to be under discussion. Everything was on the table, nothing was off the table, including ongoing projects. So nothing was taken for granted. We wanted to understand the science, and we wanted to reaffirm the case for every single project that appears in the report. It's also important to point out that this was a panel that worked together extremely well. Everyone listened to each other with respect, and we talked through all concerns, and in the end tried to optimize our recommendation to come up with a particle physics program that is really a strategic plan, and every member was thinking beyond their own individual interests. So it was clear they were on the panel for their expertise, but they were not arguing for their field or subfield or projects. There were many difficult conversations and long conversations. And last night, some of the panel members remember it, how many hours late into the night we were at various meetings this summer, working through various issues that we were facing. But the long discussions paid off. And in the end, I'm happy to say that everything that you will see this afternoon is a decision by consensus. We never made a decision based on voting. And the principle was, if the 30 of us can't agree on a plan and can get behind it, how would we expect the broader community of thousands of physicists to actually endorse it? So we have a consensus plan, and everyone in P5 stands fully behind it. Now, we have to realize, of course, there are conflicts of interest. Everyone at the beginning of the process recorded their conflict of interest, stated it during discussions. And if there were issues discussed, if you had a conflict of interest, you could make a factual contribution, a factual correction, but not express your opinion during the deliberations. A couple of words about prioritization principles before we get to the real report. In the process of proper prioritization, we considered science first. The scientific opportunities was really important. We had to combine this with budgetary realism. And in the end, we're striving for a balanced portfolio as major decision drivers. We looked at projects in different categories, large projects above 250 million, medium projects, and small projects. And of course, the characteristics of what you expect from projects at these different scales is slightly different. For a large project, you expect it to be paradigm changing, discovery potential, world leading, and of course, unique in the world. And you see that, for example, for smaller projects, you might also weigh things like excellent training grounds. Still, the science is important. We want to do things that give us new knowledge, but we weigh these things differently. Overall, in the prioritization, we wanted to make sure that we can continue US leadership in particle physics and enable this leadership in core areas of our field. We also wanted to leverage unique facilities that the US has or is building, or capabilities. We're aware of the national context, and it's important that our field engages with core national initiatives to develop key technologies. This is where we have a synergy between our field and society at large. And of course, workforce is very important. One of the benefits of the science that we do, the particle physics, is the training, development of a highly skilled workforce for the future, and that draws on all of the US talent that we have in the nation. So being inclusive, drawing on the broad set of talent is important for our workforce development. And again, the international context, engagement in the international context is important. Leadership, US leadership, but also being a partner. And that's, of course, where we also took input from the international benchmarking panel. In the end, we considered the uncertainties and costs and risks and schedule with the input that we had from J. Marks' subcommittee as part of our prioritization exercise. And we were able to construct a plan or budget scenarios that fit within a few % of the given budget scenarios. And we also ensured that there's a reasonable outlook towards the future. We wanted to make sure that what we recommend now can continue and into the next decade beyond our 10 years within the 20-year vision, and that we are not mortgaging the future. So in the end, we balance the program in terms of size and timescale of projects, onshore, offshore, project versus research, and current and future investments. And before we get to the recommendations, I just wanted to thank again the community for all the input, for being so responsive with us, providing us input, being interactive. And this P5 plan builds on the SNOMAS process and your vision that was articulated there. And hopefully it is now the plan for the community. And with that, I'll hand it over to Hitoshi, who will discuss the recommendations.
Okay, so that was Taylor Swift 1. So now come Taylor Swift 2. So I'd like to present the report itself. The title of the report is Exploring the Quantum Universe, Pathways to Innovation and Discovering Particle Physics. And so this is a report of the Particle Physics Project Prioritization Panel 2023. And come back and talk about this graphics in a few minutes, but let me get to the table of contents. So it starts with a preface, list of panel members, executive summary, and introduction. I will give you some excerpts on the introduction in the next few minutes. And then section 2 is really the recommended particle physics program. And the set of recommendations we wrote are all in section 2.2, and we try to make them short enough that I will actually show all the recommendations fully in this presentation today, and also give some more quotes from the rest of section 2 as well. And the next 3 chapters are about 3 science themes we came up with, and I'll talk about this also in a few minutes. And section 6 has investing in the future of science and technology. So this actually talks about all kinds of investments we feel are needed in terms of our field to make progress and maintain and go even better. And so in this section, we have specific recommendations called area recommendations, as opposed to the overall recommendations in section 2. And I come back and also give the full list of the area recommendations later on. And section 7 is about the workforce, which is very important. So because of the importance, all the recommendations associated with workforce are not listed as the area recommendations because that would affect the entire field. So they are included as recommendation 5 in the project-wide recommendations. And finally, in section 8, we talked about hard choices we had to make in terms of making sure the program would fit within the budget scenarios given by the funding agencies, and followed by appendix, 4 lists of recommendations and acknowledgements. So the first thing we had to do on this panel is to understand who we are, what is our science, what kind of questions we'd like to ask, what we would like to understand. And of course, particle physics has been traditionally defined as a discipline to look for the fundamental constituents of matter, looking for in smaller things that will make up everything around us. And definitely this is still the direction we want to pursue. And this is the area we call decipher the quantum realm. So the word quantum has become kind of in some sense popular, but we are the quantum or quanta, right? So we do the most small things. And so this is definitely one important aspect of the field. And we have come up with the standard model of particle physics. We discovered the Higgs boson was very important, but we still also know that the standard models is incomplete. There's still something else to be discovered. We also realized that what is rather unique about the particle physics program in this country is that it has the other leg of looking at bigger and bigger things rather than smaller objects, and that's cosmology. And in the area of cosmology, we are looking at this expanding universe, but we have discovered dark energy as part of our field, and there's still many things that are yet to understand. Of course, that is described extremely well by Lambda CDMS model, but again, we know that model is incomplete. And so this is an area of science theme we call illuminate the hidden universe, because so many hidden things in here are really driving the evolution of the universe, dark matter, dark energy, inflation, and so on and so forth. And given that both of them are incomplete paradigms, we need to look for new things which will complement the picture of this whole thing, how the universe works as a whole. And so that's an area we're looking for the new paradigms. So this is a science theme we call explore new paradigms in physics. So that's the meaning of this graphics, which we call the mural. So it has 2 legs and something in the middle. And this graphics is meant to be actually very interesting to watch. If you look at this flying obstacle over here, is both particles and waves together. You can see the hint of Higgs potential in here, and Higgs boson is stuck at the bottom of this potential. You will see dark matter driving the large structure of the universe. And then here in the bubble, the things evolve from the cosmic molecular background to stars and galaxies. In the middle, you may think of this as a particle collision, or you may think of this as a Big Bang. Many things are flying apart from this. They may be particles, primordial black holes, dark matter, maybe baby universes. So that's the way we view our field. So that's what we try to understand. And under these 3 science themes, we have science drivers, which is a natural evolution of the science drivers from the previous period. At the first look, they may not look that different, but nonetheless, they show the evolution from the previous P5. I forgot to mention that the title of the report, Explore the Quantum Universe, came from taking each one word from each science themes: quantum, universe, explore, hence explore the quantum universe. So in each of the 3 science themes, we have 2 science drivers. For example, in this in the first science driver, decipher the quantum realm, we elucidate the mystery of neutrinos. And the last P5 report talked about understanding the mass of neutrinos. But neutrino physics is much broader than the mass. We like to understand its interactions. We even don't know how many of them they exist. So we actually broaden it about the mysteries of neutrinos. And also about the Higgs boson, we say reveal the secrets of the Higgs boson rather than the Higgs boson as a new tool for discovery. So back in 2014, we had this idea that Higgs boson is such a totally different kind of particle from everything else. It should be accompanied by its own family, like superparticles and extra dimension particles. Now, we don't see them, which means the Higgs boson itself has become a much of a heightened interest. We really understand why this particular particle is condensed in the universe today. And that's why we changed the science driver to reveal the secrets of the Higgs boson and to understand what exactly is actually going on with it. And in terms of the hidden universe, we need to determine the nature of dark matter. And the previous P5 report said identify. And that was the time of thinking when we knew dark matter is probably WIMP, possibly axion. We had to identify that. So now we are looking at this enormous parameter space of possibilities about the nature of dark matter. So we really need to look broadly about that and determine its nature. And that's, again, an evolution. And understand what drives cosmic evolution. So the previous P5 concentrated on accelerating expansion due to inflation and dark energy. But there's a lot more information, for example, looking at the galaxy surface, you can extract from decelerating era of the universe as well. So again, we like to look much more broadly about cosmic evolution. And when we explore new paradigms, and that was called unknown in previous P5 report, but there are two very different approaches we can take on this. And one of them is look for the direct evidence of new particles, which of course is a hallmark of particle physics. But in addition, we can pursue quantum imprints or virtual effects for new phenomena like Muon G-2 experiments. So these are the 6 science drivers that reflect what we have learned over the years from the previous P5 report. And this mural is a little bit too complex. So for branding purposes, we drastically simplified to these 2 triangles overlapping with each other. So this side, the magenta triangle represents the quantum realm. The cyan triangle represents the hidden universe, and there's the unknown, the new paradigms at the overlap. And so each one of the science drivers are represented by these graphics in the report. And you can see the Higgs potential. This is the beginning of the universe. Higgs actually falls in as a free particle, but eventually get trapped at the bottom of the potential. And then symmetry is now broken for the rest of the evolution and so on and so forth. So each one of them had been thought through actually quite carefully, even though they're just meant to be artworks. Anyway, so that's the graphics used in the report. And we start with the introduction. Section 1 has an overview vision. This is the last paragraph in it. This is actually meant to represent what we think we have produced in this report. We envision a new era of scientific leadership centered on decoding the quantum realm, unveiling the hidden universe, and exploring novel paradigms. Balancing current and future large and mid-scale projects with the agility of small projects is crucial to our vision. We emphasize the importance of investing in a highly skilled scientific workforce and enhancing computational and technological infrastructure. Acknowledging the global nature of particle physics, we recognize the importance of international cooperation and sustainability in project planning. We seek to open pathways to innovation and discovery that offer new insights into the mysteries of the quantum universe. So the rest of the report is about how we wanted to accomplish this vision in the report. So briefly about processing criteria. So recommended programs should reflect the scientific interests of the particle physics community, enable U.S. leadership in core areas of particle physics, leveraging of unique U.S. capabilities or facilities, engage with core national initiatives to develop key technologies, develop a skilled workforce with future that draws on U.S. talent, effective engagement and leadership in international endeavors. And projects are assessed by scientific merit and potential for transformational discovery, criteria for the overall program, maturity and technical risk, balance of project timescales, holistic consideration of the cost of construction, commissioning, operations, and related research support. Then comes section 2, which is the recommended particle physics program. So this is the beginning of section 2. That's an overview. Particle physics program that tackles the most important questions in each of the science drivers maximizes its potential for groundbreaking scientific discovery. Executing such a program requires a balanced portfolio of large, medium, small projects, coupled with substantial investments in forward-looking R&D and the development of skilled workforce for the nation. Building upon the foundations laid by the previous P5, our recommended program completes ongoing projects and capitalizes on their momentum. A suite of new initiatives at a range of scales include major projects that will shape the scientific landscape over the next 2 decades. The prioritized time sequencing of recommended projects in R&D, summarized in Figure 1, I will show that later, reflects our current understanding of the scientific landscape and its associated uncertainties. The overall program is carefully constructed to be compatible with the baseline budget scenario provided by DOE. To achieve that, we recommend continuing specific projects, strategically advancing some to the construction phase and delaying others. As shown in Figure 1, in some cases, individual phases or elements of large-scale projects have to be prioritized separately. The process and criteria by which we recommend the initiatives was selected are laid out in section 1.5. And we can also come back and talk about how we have to make our choices and what the rationales have been in section 8, if in response to some of the questions later on. I will not read the rest of the overview section because it's too long to do that. So now I jump to section 2.1, which shows the recommendations. And there are actually 6 of them. So to drive U.S. particle physics forward and maintain strong global leadership, we advocate a comprehensive and balanced program that strategically addresses the 3 science themes and their 6 interwoven drivers. The numerical order of the recommendations listed below is not meant to reflect their relative priority. Instead, it is used to group them thematically. The lists under the recommendations are not prioritized, except for the list of major projects under recommendation 2, and you'll see that in a moment. Each recommendation is stated in boldface, followed by concise lettered explanations of how the recommendation can be realized. The impact of alternative budget scenarios on a different elements of the program is discussed in section 2.6. I'm going to actually show that as well. And a full list of recommendations provided at the end of the report. That list includes area recommendations from section 6 I alluded to earlier, in addition to those 6 recommendations here. So starting with the recommendation 1. As the highest priority, independent of the budget scenarios, complete construction projects and support operations of ongoing experiments and research to enable maximum science. We reaffirm the previous P5 recommendations on major initiatives, high-lume LHC, including Atom CMS detectors, as well as accelerator upgrade project, to start addressing why the Higgs boson condensed in the universe, and that's part of the science team of Driver, review the secrets of the Higgs boson. To search for direct evidence for new particles, to pursue quantum imprints for new phenomena, and to determine the nature of dark matter. Second, the first phase of Dune and PIP2 to determine the mass ordering among neutrinos, a fundamental property in a crucial input cosmology and nuclear science, and mass hierarchy, of course, determines the overall scale of the neutrino masses and how that would compare to the future measurements from cosmology and the mobility decay and direct measurement of the neutrino mass would be very, very interesting tests of the fundamental paradigm there. And the VLC Rubin Observatory to carry out the legacy survey of space and time and LSST dark energy science collaboration to understand what drives cosmic evolution. And this is yet to be completed, even though DOE side of the project to complete the LSST camera is done. The telescope itself is not in operation yet. So this has to be completed first so that we can get on to the major initiatives in science. In addition, we recommend continued support for the following ongoing experiments at the medium scale, and including completion of construction, operations, and research, NOVA SB short baseline, P2K and IceCube on neutrinos, DarkSide 20K, LZ, Super CDMS Xenon, and TON on dark matter, DESI on cosmic evolution, BEL2 LCB and Mu2E on quantum imprints. And the agency should work closely with each major project to carefully manage the cost and schedule to ensure that U.S. program has a broad and balanced portfolio. Namely that if something goes unfortunately wrong, that will start impacting the rest of the program. So this set of projects need to be managed very, very carefully so that the overall balanced portfolio can be maintained. Recommendation 2, construct a portfolio of major projects The collectively study nearly all fundamental constituents of the universe and their interactions, as well as how those interactions determine both the cosmic past and future. These projects have the potential to transcend and transform our current paradigms. They inspire collaboration and international cooperation in advancing the frontiers of human knowledge. Plan and start the following major initiatives in order of priority from highest to lowest. And this is the only recommendation which has a rank order priority among the projects we are recommending. So there are 5 of them. The first priority is CMBS-4, which looks back at the earliest moments of the universe to prove physics at the highest energy scales. It is critical to install telescopes at and observe from both the South Pole and Chared sites to achieve the science goals. And we talk about its rationale in section 4.2. Second priority is re-envisioned second phase of Dune. With an early implementation of an enhanced 2.1 megawatt beam, which is called ASMERT, accelerator complex evolution, main injector, and the main injector. Ramp and target R&D. Sorry about that. Third fault detector, an upgraded near detector complex as a definitive long baseline neutrino oscillation experiment of its kind. So this is in some sense the ultimate experiment we can imagine of doing neutrino experiments based on neutrino superbeam technology. If you're going to be on that, that will require a totally new kind of technologies. And priority number 3 is an offshore Higgs factory, realized in collaboration with international partners in order to reveal the secrets of the Higgs boson. The current designs of FCCEE and IOC meet our scientific requirements. The US should actively engage in feasibility and design studies. Once a specific project is deemed feasible and well-defined, the US should aim for contribution at funding levels commensurate to that of the US involvement in the LHC and high-LUMI LHC, while maintaining a healthy US onshore program in particle physics. So we should stay engaged, and FCCE and IOC meet the requirements. So once they're going, we would like to be on board. But we need to have a process to define what our contributions should be. And I'll come back and talk about this in recommendation 6. And it also needs to be done at the level that we are a strong partner that puts some lower bound on contribution. But also we need to maintain healthy onshore program, which puts some upper bound on it. And you'll see the cost range in one of the tables later on. The fourth priority, an ultimate generation 3 dark matter direct detection experiment, reaching the neutrino fog in coordination with the international partners and preferably sited in the United States. And the neutrino fog is a irreducible background for the search for WIMPs. So this is a reachable goal. So that's a milestone we can get to. We like to get there. But once you reach that the level of this reducible background, you presumably stop and think what to do next. So that's why we are calling this an ultimate experiment of this kind. And the preferred site in the US that would actually also require the outfitting of the expanded caverns at surf. The fifth priority is IceCube Gen 2 for study of neutrino properties using non-beam neutrinos complementary to Dune, and for indirect detection of dark matter covering higher mass ranges using neutrinos as a tool. And what's common between CMBS-4 and IceCube Gen 2 is that both of them require the infrastructure at South Pole, which again, we'll come back and talk about this in a moment. So these 5 projects are the recommendations in this priority order. And the principles can be found in sections 1.6 and 8.1. And we would like to also add the IceCube Gen 2 has a strong science case in multi-messenger astrophysics beyond interesting particle physics, together with the gravitational wave observatories. We recommend that NSF expand its effort in multi-messenger astrophysics, a unique program in the NSF division of physics, with US involvement in the Cherenkov telescope array, a next-generation gravitational wave observatory, and IceCube Gen 2. Namely that we evaluated these projects through the lens of particle physics. We still came up with them on a priority list, but there's a whole lot more science case beyond what we could evaluate. So we just want to highlight that fact in this narrative in recommendation 2. So that gives us this the chart of the potential timeline of various projects, and each project addresses one or many of these science drivers indicated by P for primary and S for the secondary. And each of them would move from the R&D phase to construction phase and operation phase. And that's the time chart you can see in the report. Recommendation 3, create an improved balance between small, medium, large scale projects to open new scientific opportunities and maximize their results, enhance workforce development, promote creativity, and compete on the world stage. In order to achieve this balance across all project sizes, we will recommend the following. Implement a new small project portfolio at DOE, advancing science and technology through agile experiments, and ASTE for short, across science themes in particle physics with a competitive program and recurring funding opportunity announcements, ideally annual. This program should start with the construction of experiments from the Document New Initiative, DMNI, by DOE HGP. And ASTE, I'm not well educated on this, apparently means it means something in Latin, which were known to some of the well-educated members of the panel, and ASTE means javelin. So you can quickly address a particular target quickly, and that's the meaning of ASTE program. B, continue mid-scale research infrastructure, MSRI, and major research instrumentation, MRI programs as a critical component of NSF research and project portfolio. So this is already happening, and we are very happy about that. So we recommend NSF to continue in this effort, possibly expand it. And C, support DAISY-2 for cosmic evolution, LSCB upgrade 2, and BEL-2 upgrade for quantum imprints, and US contributions to Global CTA Observatory for dark matter. And so these are relatively small, mid-sized scale projects, and we're recommending them. And BEL-2 recommendation is not just about the detector, but also includes contributions to a Super K-Kibi accelerator, where you can gain a valuable experience dealing with the nanobeam technology, which may actually pave the way to things like FCCEE in the future. So this is the way we would like to maintain a good balance among large, medium, and small scale experiments in our portfolio. Now, recommendation 4, which is actually investment into the future. Support a comprehensive effort to develop the resources, theoretical, computational, and technological, essential to a 20-year vision for the field. This includes an aggressive R&D program that, while technologically challenging, could yield revolutionary accelerator designs that chart a realistic path to a 10 TeV Parton-Senov Momentum Energy Collider. That's a new acronym. So Parton-Senov Momentum Energy. Investing in the future of the field to fulfill this vision requires the following. It's a bit of a long list, but we felt very strongly about all of them. A, support vigorous R&D toward a cost-effective 10 TeV Parton-Senov Mass Energy Collider based on proton, muon, or possible wake field technologies, including an evaluation of options for US siting of such a machine with a goal of being already built major test facilities and demonstrator facilities within the next 10 years. And we mean this as a very aggressive path to develop this kind of technology. And we are showing aspiration to eventually host such a machine on the US soil if everything goes well. So that's the first recommendation on this list. B, enhance research in theory to propel innovation, maximize scientific impact of investments in experiments, and expand our understanding of the universe. And when you go to area recommendations, I'm going to show you later on, we are very specific at the level of the increase we are asking for in terms of dollar amount. C, expand the General Accelerator R&D Guard program within HEP, including stewardship. Again, if you go to area recommendations, you see specific figures in the content. D, invest in R&D in instrumentation to develop innovative scientific tools. And once again, there's an area recommendation for that too. E, conduct R&D efforts to define and enable new projects in the next decade, including detectors for an A+U- Higgs factory and 10 TeV Parton-Senov Momentum Energy Collider, Spectrus 5, Dune FD4, Mu2E2, Advanced Muon Facility, and line tensor mapping. So again, you see specific description of that in later sections. F, support key cyber infrastructure components such as shared software tools and a sustained R&D effort in computing to fully exploit emerging technologies for projects. Prioritize computing and novel data analysis techniques for maximizing science across the entire field. There are 4 area recommendations for this item. G, develop plans for improving the formula accelerator complex that are consistent with the long-term vision of this report, including neutrinos, flavor, and 10 TeV proton center mass energy collider. And I will show you some description on what our vision is along this line in a few minutes. We recommend specific budget levels for enhanced support for these efforts and their justifications as area recommendations in section 6. You'll see the full list of that. So including these investments, so this timeline chart has the bottom part of this chart, which shows how much we like to invest and when in terms of assay and various small scale and medium scale experiments, planning for the future, and also 4 areas where we felt that there's some new reinvigoration needed to make sure that we maintain U.S. competitiveness, namely accelerator, theory, instrumentation, and computing. Recommendation 5, invest in initiatives aimed at developing the workforce, broadening engagement, and supporting ethical conduct in the field. This commitment nurtures an advanced technological workforce, not only for particle physics, but for the nation as a whole. So here are the 5 recommendations we feel are actionable recommendations to the agencies. A, all projects, workshops, conferences, and collaborations must incorporate ethic agreements that detail expectations for professional conduct and establish mechanism for transparent reporting, response, and training. These mechanisms should be supported by laboratory and funding agency infrastructure. The efficacy and coverage of this infrastructure should be reviewed by a HEPAP subpanel. B, funding agencies should continue to support programs that broaden engagement in particle physics, including strategic academic partnership programs, traineeship programs, and programs in support of dependent care and accessibility. A systematic review of these programs should be used to identify and remove barriers. C, comprehensive world climate studies should be conducted with the support of funding agencies. Large collaborations in national laboratories should consistently undertake such studies so that issues can be identified, addressed, and monitored. Professional associations should spearhead field-wide world climate investigations to ensure that the unique experiences of individuals engaged in smaller collaborations and university settings are effectively captured. So not only the large collaborations in laboratories, the small settings should also be captured this way. D, funding agencies should strategically increase support for research scientists, research hardware and software engineers, technicians, and other professionals at universities, because we feel they're a very, very crucial aspect of keeping the training of the young generation going. E, a plan for dissemination of scientific results to the public should be included in the proposed operations and research budgets of experiments. The funding agency should include funding for the dissemination of results to the public in operation and research budgets. And we understand that this cannot be included in the construction projects, but for operation and research budgets, they should be included, and that is our recommendation. And last recommendation, number 6, convene a targeted panel with broad membership across particle physics later this decade that makes decisions on the U.S. accelerator-based program at the time when major decisions concerning an offshore Higgs factory are expected, and or significant adjustments within the accelerator-based R&D portfolio are likely to be needed. A plan for the Fermilab accelerator complex consistent with the long-term vision in this report should also be reviewed. So this new panel would consider the following: the level and nature of U.S. contribution in a specific Higgs factory, including an evaluation of the associated schedule, budget, and risks, once crucial information becomes available. And crucial information may be the outcome of the feasibility study of FCCE, or the discussion by international development team on IOC to frame the global formulation for the project. And once such a crucial information is available, then U.S. should be engaged and talk about what we can contribute. 2, mid and large scale test and demonstrator facilities and accelerator and collider R&D portfolios. So we recommended aggressive R&D program for accelerator and also for the targeted R&D for the future colliders. And many of these things will come up with a more concrete design. For example, International Muon Collider Collaboration is trying to come up with a reference design report before the European strategy update expected in 2025 or 26. So that will be the basis of the decision by this panel where we should go beyond that point. So that's a decision on test and demonstrator facilities that may take in sort of the mid-decade a new panel. 3, a plan for the evolution of the Fermilab accelerator complex consistent with the long-term vision in the report, which may commence construction in the event of a more favorable budget situation. So we did not recommend the booster replacement within this 10-year period. But if there is a better plan that is consistent with the long-term vision, and if the budget scenario turns out to be more favorable, that can in principle be recommended by this panel. And so the reason why we recommend such a panel is that we don't want till the next P5 make these major decisions. That's why we're recommending a new panel. But presumably it doesn't need to be accompanied by the full snow mass update because that's a huge undertaking. And many of these things have been already looked at by the previous snow mass process. So we know what the science cases are. So without snow mass, but with a new panel in a timely fashion, we hope this kind of decision can be made so that field can make progress fast in aggressive fashion. So that's our recommendation 6. And we kept talking about this long-term vision for the field. So there's a section 2.3, which talks about the path to a 10 TeV partner center mass energy. Realization of future collider will require resources at a global scale and will be built through a worldwide collaborative effort where decisions will be taken collectively from the outset by the partners. So that we really listen to the international benchmarking report that decision has to be made from the outset in the international collaboration. This differs from the current and past international projects in particle physics, where individual laboratories started projects that were later joined by other laboratories. The proposed program aligns with the long-term ambition of hosting a major international collider facility in the US, leading the global effort to understand the fundamental nature of the universe. In particular, a Muon collider presents an attractive option both for technological innovation and for bringing energy frontier colliders back to the United States. The footprint of a 10 TeV partner center mass energy Muon collider is almost exactly the size of the Fermilab campus. A Muon collider will rely on a powerful multi-megawatt proton driver, delivering very intense and short beam pulses to a target, resulting in a production of pions, which in turn decay into muons. This cloud of muons need to be captured and cooled before the bulk of muons have decayed. Once cooled into a beam, fast acceleration is required to further suppress decay losses. We don't have this technology at hand today, so it really needs to be developed. Although we do not know if a Muon collider is ultimately feasible, that's why we need to do R&D, the road toward it from current Fermilab strength and capabilities to a series of proton beam improvements and neutrino beam facilities, each producing world-class science while performing critical R&D towards a Muon collider. So we don't know a Muon collider is possible, but working toward it comes with high reward because that would enable many things on its way. At the end of the path is an unparalleled global facility on US soil if this pans out. So this is our Muon shot, and that is our long-term vision. 2.4, stewardship of key infrastructure and expertise. And I'm not going to read all of them, but we highlight the importance of DOE national laboratories, especially true for Fermilab as the only dedicated US laboratory of particle physics. South Pole, which is a unique site that enables the world-leading science of CMBS4 and ice cube Gen 2, must be maintained as a premier site of science to allow continued US leadership in these areas. Given that both of these projects are on the high priority list, we really hope that the NSF Office of Polar Program would work with us to making sure that this infrastructure can be updated to support these projects. And SURF, also has a tremendous support from South Dakota and private donors, which is now also undergoing an extra excavation. And the outfitting of the cavity would be a DOE responsibility. So we're recommending that as well. And GOD program, General Accelerator and R&D, is critical in supporting a broad range of accelerated science and technology for DOE Office of Science, separate from the targeted R&D toward future colliders. And along with NSF-funded fundamental accelerator science, GOD supports the broad workforce. So this is actually a very important area where we have to keep spending on and play the role of the stewardship. And international interagency partnerships, again, I don't read the whole thing, but here's a repeat sentence. A dedicated panel should review the plan for a specific Higgs factory once it is deemed feasible and well-defined. So this is a major part of our thinking. And in parallel to the R&D for Higgs factory, the U.S. R&D effort should develop a 10 TeV proton center mass energy collider design and technology, and aiming for demonstrator facilities within a 10-year timescale so that we can develop this technology in an aggressive and timely fashion. And we already talked about this. Now comes a very difficult question. It's been really difficult to make hard choices for the baseline scenario, but if the budget scenario is less favorable, that becomes even more difficult. In this scenario, we would aim for a program that covers most areas of particle physics for the next 10 years, maintaining continuity and exploiting the ongoing projects in recommendation 1 as our first priority, namely ongoing projects. The agencies should launch the same major initiatives as outlined in recommendation 2, namely 5 major projects, some of them with significantly reduced scope. CEMBS 4, we didn't see any way that can be reduced in scope, so it should be maintained because it's the highest priority anyway. Dune, third part detector should be built, but we decided to defer MERT and more capable near detector, MCND. Without MERT, we don't have enough statistics to justify MCND. So the third part detector is the one we recommend. Contribution to an offshore Higgs factory, but our contribution will be delayed and also be at the reduced level in this scenario. The reduced operation in offshore G3 document experiment. Remember, we recommended G3 document experiment to preferably on the US site, but now we are saying it may need to go offshore because we will not be able to support onshore program in this regard, and that would nullify the need for source expansion at the same time. And E, IceCube Gen 2, this one without reduction in scope. So this is what we need to do to make even harder choices in this less favorable budget scenario. And the rationale for this prioritization is given in section 8.3. And I don't read through everything here, but recommendation 3 and 4 are crucial for maintaining health and balance of field, so they should stay. But they should be actually reduced in the funding levels proportionate to maintain the balance we have proposed in these recommendations. So it's not that they will go down the drain, they should be reduced proportionally. Recommendation 5 on workforce is deemed high priority in supported in all scenarios, no matter how bad the funding may be. And recommendation 6 of having this new panel mid-decade applies in all scenarios. But overall, this funding budget scenario will lead to a loss of leadership in many areas. So we really hope that we can work with agencies to make sure that this scenario is not what we're going to get over the next decade or so. The chart didn't ask for any discussions what we could do in a more favorable budget situation, but we volunteered to say something about that anyway. And in this case, because there is no specific budget scenario, all we can do is come up with a menu without knowing how more favorable the budget scenario may be. So the menu starts from the small scales, we're going to the larger scales later on. And the smaller scales, that's mostly R&D, increase investment in detection and R&D targeted towards future collider concepts of Higgs factory and 10 TeV machine in order to accelerate US leadership in this area. Pursue an expanded DOE accelerated science and technology initiative to develop foundational technologies for particle physics that can benefit applications across science, medicine, security, and industry. pursue broad accelerator science and technology development at both DOE and NSF, including partnerships modeled on the Plasma Science Partnership. So that's a category of small-scale R&D. What we can add as a project is to expand the portfolio of agile experiments ASTE to pursue new science, enable discovery across the portfolio of particle physics, and provide significant training and leadership opportunities for earlier career scientists. Now, moving up to an even larger scale of medium projects, initiate construction of SPEC-S5 as the world-leading study of cosmic evolution with applications to neutrinos and dark matter once its design matures. Initiate construction of advanced fourth far detector for DUNE that will expand its neutron oscillation physics and broaden its science program. And we call this fourth module far detector as a module of opportunity described in a later section. Initiate construction of second G3 dark matter experiment to maximize discovery potential when combined with the first one. And now going to the largest scale, evolve the infrastructure of the Fermi-Lab Accelerator Complex to support the future 10 TeV Hadron Center Mass Energy Collider as a global facility. A positive review of the design by a targeted panel I discussed in the context of recommendation 6 may expedite its execution. So recommendation 6 would review the plan that gets developed by a task force at the Fermi-Lab in the several year time scale. And if that plan is deemed good, and if the funding scenario is also good, then it is good in principle commence construction following this recommendation. So that is what may happen when the budget scenario is more favorable. And we try to summarize all these choices into a single table here, which we call the figure 2. And what's shown in black is unfortunately something we cannot recommend. And you see quite a bit area of the black or gray, which means that we have to make many hard choices. And the project we recommend are shown in yes. And C is actually a conditional yes, because we need to review what the aspect of that is before we can say go ahead. That includes accelerated test facilities and demonstrators by this new panel we recommended in recommendation 6. And depending on the funding scenarios, some of the projects do not go ahead right away, but need to spend in R&D phase for some time before they can be reviewed and go to a real construction project. So that is our recommendation. And just to understand how we stack up against the wish from the community, this is the wish list from the community in the highest summary report of the SNOWMAS study. And we actually, of course, shoot a lot on what we can do about this wish from the community. And in the recommendations we have just outlined, we do support U.S. initiative for the targeted development of future colliders and their detectors. We do support involvement in offshore Higgs factory. We support the current phase 1 of DUNE and PIP2. And we do support re-envisioned phase 2 of DUNE with MERT and third far detector. We support cosmic microvacuum stage 4. We support multi-scale dark matter program, starting with DMNI as the initial set of projects for ASTE, and also the G3 dark matter experiment. And we do support R&D for spectroscope survey S5. Unfortunately, we couldn't actually put that into the baseline budget scenario. Also, the scenario presented to us didn't appear to be mature enough for us to be able to recommend it right away. So they need to come up with a more refined and specific scope, and so that can be reviewed later. And as I said already, if the budget scenario is favorable, this could, in principle, commence construction within the next decade. And we recommend R&D for line intensity mapping, R&D for advanced muon facility. For the next generation gravitation wave observatory, we were not quite sure if that is really within the portfolio of particle physics. So we are recommending a stronger study from the theory side to see what kind of gravitational wave observatory is consistent with the vision and scientific interest of the field. So that is a study we are recommending in this context. So you see check marks given to pretty much every aspect of this highest level recommendation of SNOWMAS. And we had to go through a lot of sort of creative thinking, as I outlined in a discussion, to make sure that all of these things can fit within the budget scenario. So this red curve is a baseline budget scenario from DOE. now shown in $23. And you see the evolution of the budget for research, projects, and operations. And what he described in his recommendation really fit within this profile with a rather few error bars you can see at the very top. And we talked a lot about balance. And so I'd like to also show what is the rebalancing that is taking place based on our recommendation. And I have to put in caveat here, this is a snapshot in 2 particular years. This is year 2023, which has just finished. And this is the year 2023, that's the last year within the purview of a recommendation. So this is the beginning and end. And every year is different. So this is not meant to be representative in any way, but at least want to get across the idea what we mean by balanced portfolio. So right now, our budget is pretty much saturated by Dune. The gray intensive frontier is basically Dune, and this yellow is formative accelerator, that's PIP2, that's also basically for Dune, and small component going to energy frontier, Atlas and CMS. At the end of the decade, you see much more colorful pie chart. So this is the energy frontier because the Higgs factory construction will start to ramp up if everything goes well by that time. Test facility and demonstrator, we talked about start building those things within this decade. So hopefully that's happening here. Intensive frontier, again, is mostly Dune, but this re-envision phase 2 that is ongoing. And this is the formative accelerator because we need to invest in MERT. So that is crucial component of a recommendation for phase 2 of Dune. Red in Cosmic Frontier, this is primarily CMBS4 and the G3 dark matter experiment. And this, I don't know how to call this color, sort of a dark pink, small project portfolio that's ASTE we talked about. So initially that is also mostly for dark matter, but it's not restricted to. And this light pink, possible new projects. So by the end of the decade, we start to see room for something new that may happen beyond the recommendations. So that's a change from this year to 10 years later. And this is where the way we at least wanted to highlight. We came up with a balanced portfolio in our program. And in addition, we have these area recommendations, and I'm already speaking nearly 40 minutes, so I'd like to, I will not read everything, but you can see an example, like in theory, we are recommending specific figure. And the agency might feel like we are a bit too micromanaging, but at least we want to indicate what is the level we think is justified in 4 targeted areas of research. And we are not asking for just to boost entire research portfolio proportionally. We identified 4 areas we feel very strongly about: theory, accelerator, computing, and instrumentation. And we also wanted to indicate what is necessary to really invigorate these areas so that we want to justify the increase in research bottom up, not top down. And that's why we are providing these explicit dollar figures in each of them. Design of ASTE is supposed to be broad, predictable, and recurring, preferably annual call for proposals, so that people would know when they can submit a new proposal. And it's supposed to be about $35 million per year in supporting these small-scale experiments. And we talked about need for project management through different phases of the projects. And DM&I projects should be the initial suite of ASTE portfolio. Instrumentation, again, explicit figure here, and that's strongly leverages on national initiatives such as QIS, microelectronics, and AIML. GUARD, again, specific figure. And we're talking about small test scale facilities initially, and then moving on to much more major facilities later on. Collider and R&D, again, we are recommending specific figure, for example, an R&D for collider detector, and also collider accelerator, so that we can put together an aggressive R&D portfolio in this area. Facilities and infrastructure, so this is actually broken down into what kind of facility we are talking about. So to successfully deliver major initiatives in leading global projects, we recommend the national laboratories to have efficient remote and on-site collaboration, facilitate procurement processes, and provide robust technical support, and create a supportive, inclusive, and welcoming culture. That's for the national laboratories. And in the case of Fermilab, there's also a specific recommendation about this forming this task force. And this is coupled to the recommendation we made earlier that we're asking Fermilab to come up with a plan for the accelerated complex evolution that is consistent with this vision going towards the 10 TeV center-mass energy collider in the future, while maintaining the enhanced infrastructure on its way. So that's the task force we are asking for. And also we like to make sure while Dune is working full steam, especially after the motor upgrade, we need to provide a reliable operation of the booster. So the Fermilab and the agencies need to pay active attention on the related system to reliability risks and preemptively address these risks. And we learned that this can be done at a relatively modest cost compared to the full replacement of booster. So that is a recommendation. And coming back to the issue of South Pole, the infrastructure really need to be provided to support our major recommendations and CMV S4 and IceCube Gen 2. So that is also recommendation down here. And software computing cyber infrastructure, we have these 4 recommendations, again with explicit dollar figures here, and connection to AI, ML, quantum computing, and microprocessor, of course, is obvious and important. And support the research software engineers and other professionals and university labs are also important in the concept we talked about earlier. And let me also highlight that kind of cyber structure we are talking about also includes support for particle data group and INSPIRE database, which we have to rely on everyday research. So that's part of the recommendation as well. And the last area recommendation, number 20, KEPAP, potentially in collaboration with international partners, should conduct a dedicated study aiming at developing a sustainability strategy for particle physics. And that, of course, is an important subject in today's world. So that is the gist of a report. And I'd like to acknowledge and thank many people. And I don't go through this whole list, but highlight the very end. We thank APS-DPF for organizing SNORMAS community study and all members of a community for their bold and creative vision, as well as their input to the process. So without this input, of course, we couldn't have done our work at all. So we'd like to thank everybody in the community. I also would like to acknowledge people on the panel who were present at this meeting. And of course, Carsten has been my very reliable deputy. And I'd like to have all the P5 members to stand up so that everybody can recognize you. Jesse, Maylee, Amanda, Bob, Mark, Cameron, Peter, Patrick, and Chris, and Christos, and May, Yelena. So, if you like our report, please comment them. But if you don't like our report, I will take all the tomatoes I can get. Thank you for your attention. I guess back to Sally.
So we're going to take a 15-minute break. I think many people might know that the Zoom session maxed out at 500 participants, and it's causing a significant concern in our community. And at this time, our best way to address that is to promote people who are attendees to be panelists. So at this point, about 100 attendees have received requests to change their status as panelists, and that will leave spaces for more people to join as attendees. Unfortunately, only 3 people who received those requests actually accepted them. So if you're online and you received a request to promote to panelists, please accept it to make room for additional people to join. So we'll take a break now until 2:30.
That's my person.
Well, we did okay.
So Bertrand and I will now do our happy dance. Yeah.
So any thoughts and comments? I think it's a discussion lunch, right?
I thought I didn't have the IceCube Gen on my radar. They really strongly supported that.
Yeah.
I think it's pretty balanced. It's hard to disagree with that.
What are you gonna, right, so they didn't endorse the Muon glider, which they sort of said you should do online.
Yeah.
They said, we're gonna do it. LHC phase, HLLHC upgrades. They're gonna continue with Dune, but not in a crazy way.
they did not support the Fermilab accelerator complex
Right.
upgrades.
Right,
That's probably
because
the
they're-
biggest
they
impact
said
of
they're
Fermilab.
ready, which-
And true.
Right, and so hydromonopsony and LHC finished doing, and there's no money left, and then it said everything else is R&D.
And then they had general statements about mid-scale projects that opens the door to get new things on the roadmap that aren't completely mapped out yet. I think it's great.
And all we ever asked them for was the number I didn't board R&D from AMS.
Yeah, that's all we
Needed it.
want.
35 million, 50 million.
Yeah.
I mean, I'm not.
I like that they called out Fermilab site access policies on site 50, slide 52.
During their thing.
We're actually fine.
You always need to know on being
I know.
Some characters, good computers.
Yeah, right, like, if you're starting it elsewhere, you might not know. We're talking like, we're talking about a random.
You guys are, we should, I mean, the problem is that we should.
Somehow doubt that.
On theory with my peers.
But they would just run against.
They would.
I mean, the point of what I mean is they would throw that point out. Like, are you kidding? This is crazy. You guys are.
Well,
Because the amount of cutting we've done compared to the cutting they've done.
yeah,
So much.
what they said, I want to.
Yeah, exactly.
What they said was. They're not
So I love the way Hitoshi said it. It may look like micromanagement, but we wanna, let's make a scale of what we're asking for. It is micromanagement because it's a micromanagement.
When I saw that, I go.
Yeah, they should.
Good formula. It was good, except they wanna do the booster right now. I mean, But the argument for it was always, we have to do it at some point. I think it keeps saying it's 50 years.
Became a frontier.
It's working. You know, why are they gonna break tomorrow? If it didn't break yesterday. And they say, oh, it's 50 years old, we think my roof is healthy.
I mean, the other thing is.
And they wanna do it tomorrow. It's challenging. I've never understood the argument. Now, they've sorted through it. But June phase two, but that's like.
No, basically, they're saying.
But it's weird because phase two is simply a second attempt of being. Yeah, he's talking about a third. So I don't understand where the second one went.
It never gets.
Or three more liquid argon stations in the end. But I thought it was like. First two. That's what, yeah, so they're planning one of 14. So they're the
Answer is, I don't really want to, what's a hit? That's a 55. Sorry about that. That's okay. So nothing. Yes, I did.
It won't be more so, but you never heard anything. They don't want it exactly.
I think it's said, he will not be involved in Fermi Labs, biological warfare.
Right. I have a proposal right now. For R&D.
Very small entity. So this sort of cuts off the. Oh, you're not gonna. I can see three is didn't require, I don't know, I'm trying to read it.
And Higgs, they vary specifically only to IOC.
Yes.
Yeah, they're like very clear.
Yeah,
Like,
those-
here's the two.
yeah.
Here's the two offshore, yeah, I didn't even think about this.
It's getting internal review.
Oh,
Yeah, I think so. I think it's an implicitly, I think, it's my guess, okay?
I want to let the people.
I'm not educated.
No.
By
By the way.
Oh, I'm sure they thought it was.
Yeah, I'm sure it's all of everything I listen to. So I think it is a way of.
Somewhat, it's kind of.
Right.
So I don't know.
AMF, is it a new?
That was what Bertrand was talking about. That's what I was-
I didn't understand it. Was it a new facility inside Fermilab or is it just entirely new thing?
Gravitational waves, that seems
It's
like.
a way to go.
Oh, what the name is. Right.
It's made more and more.
Yeah. I mean,
That's
really more abstract. Yeah, I think that's
cold.
I think it's a.
I think cold muons.
Yeah.
Slimmer targets.
Well, I mean, it takes away so many constraints, like what
They
parts you can
specifically
use.
mentioned
Right.
like
Like a more of a target thing.
That was,
Like the
I
question.
felt like that was.
Right.
I think it was a little surprising. But.
But
yeah, I
I'm
mean,
always
they
wondering,
definitely-
why not just go for the heaviest thing that you?
Yeah, I mean,
And
certain
not
things
actually any
have
reason.
ways, right? Or there's something,
Probably
right?
not even the best strategy.
Yeah, I mean.
There's
well, like-
so much more wavelength
I don't
of
know,
black
like,
inside the
just-
nucleus.
Yeah.
And it's a lot easier to make those
Besides that, they're
transitions.
not super expensive.
Mm,
That's probably like a medium.
Not necessarily that. I mean,
You would think.
the nucleus is a nasty thing.
I know.
Alright. The small projects. Yeah, and also specifically, I think.
It,
we
you know, it
emphasized
kind of
several
depends
times
what you want
that
to
they
do,
want
but
to
you do
start
want the
with
flexibility to change.
The goals are their new initiatives or whatever.
Because things.
Yeah, what exactly?
And choose that, that's a good factor.
I don't know, but it's.
Even
I
more
think
than
maybe
just,
it was- With respect to some
you know, to make the life.
I can't remember, but it was like, it's some enumerated already
Well,
set
aluminum.
of, like, there's small scale.
That's-
You know what? We should, yeah.
Gold used to be the thing.
Even back in the old days, when hadron experiments, we used to be called.
Yeah. You know, we should try to find out exactly.
Because it's light
What
and
just
it's
got
also
on.
easy to work. You know, like.
You know, we need to write.
Brilliant targets.
Yeah, I know this.
Yeah, but everything you were doing.
Kind of-
Yeah, I mean, come on. Yeah. No, I mean, the nice thing about this is.
You would-
So when you're writing theory papers about stuff, it was
A lot better. Gold. Silver.
Well, if you want to just drink.
Aluminum oxide is very, the outside is the aluminum, the inside. But that's before.
Yeah. Let's
go
go through that.
Yeah, today was nice.
Things.
Yes.
In the afternoon.
You guys notice
To
there
work
was
on my
no
class.
Oh, of course.
I assume that's like wrapped up in.
This
small
2 to 4 talk
projects.
is good. That's the last one. It's also something.
Yeah, that is true, like, you know, like
I see
EDMX is
about
maybe
this,
not a small project.
Dynamic, what do you call it?
Yeah, I guess,
Hand
yeah, I didn't think
devices.
about that once.
For example, we talked about this, right?
But
The
they-
starting
they did-
salary
they
for a
did follow
postdoc is like 60 to 70,000.
Well, I think they wanted to leave it.
Here, I don't, it's higher for the national labs are higher.
Well, let's
Over
say
across the board.
average. Let's say 70.
70,000 is kind of an average.
Yeah, there's more to that.
Okay, so it's even higher.
Yeah.
What about
We
the
should-
university?
We should, the next.
What do you start out with?
We don't answer the.
next month.
I actually don't know right now.
Yeah.
There's
There's no paper that's gonna come out that's gonna be more important than these 100 pages, so next week it was pages 1 to 10. And the next week, no break, no holidays, cancel your.
And the end is the top.
You have to read through it as a
Again,
group,
physics.
the whole 100.
Is there an end to it?
Yeah, there's 100K to 101K.
That's great.
That's awesome.
You're telling me.
I would really be careful about what.
I'm telling you.
Yeah. I was surprised honestly that he was saying
It
a
would
few
get
things
200.
sometimes in between.
Yeah.
It would.
Oh, which is like, I'm used to from the coach, he's trying to clarify.
And if you're in the medical school.
So I was
it's
like,
over
okay,
half.
this is getting it, but I was like,
That's
yeah,
not
actually
possible.
surprised that he was ad-libbing it on some of the.
But the salaries are pretty fast. Because, you have to
Yeah.
pay.
Yeah.
Commentary. You can't let the.
Well, cause I mean, yeah, cause I mean,
You
he's,
can't
he's,
feel like the
I
coach
mean,
got
this is
started
like
to
the presentation.
Graduate students, well.
Well, you
know,
do it
like-
to us.
Yeah, of course.
It's gotta be exactly to the word.
Gotta give me more money for the thing.
I know, you have a habit you have to support.
Yeah, most students love.
It's an addiction. It's like mess.
Right.
It's even worse than that.
You could just
Gotta
say,
get
oh,
another
don't worry.
But it's good. It's good.
Anyway, so, the salaries are okay.
Oh, yeah, I'm glad.
Significantly higher.
Yeah.
No, it's not that one, like, I'm talking about this A's, the technical tools stuff.
Oh, yeah.
Yeah, also.
But it all goes to the coaches. The coaches in the medical school.
And law, of course.
Yeah. I think the lawyers don't get as much as the medical.
Those are the ones, with no.
No,
It's been a lot of effort.
It's like one or two people though.
Oh, it's more than that.
I'm glad that Bertrand is 1/6 of all of the major lives.
There are a lot.
I should go to football.
You should be.
Yeah.
Pretty good.
Say goodbye to physics.
No.
No?
What were the?
No, that was very strict no.
If you wanted to do particle cosmology, I wouldn't criticize it one bit.
Okay.
But what have you got against
Here, there's
football
dark
coach?
matter and.
I mean, yeah.
$4 million a year? Come on, that's not bad.
And then what was,
One
what was the
Nobody
two,
makes that.
the two in the middle?
Really? That was the number I heard.
University president makes significantly less than.
In many
One
years.
Yeah.
Oh, yeah, directly detecting, yeah.
Which is
That should be
ridiculous.
so much.
He was
Yeah, I mean, we're already.
People who do the real work.
I feel like, yeah, I feel like.
Like a
probably
graduate
good amount of
student, right?
Yeah.
Instead of paying us peanuts.
Pretty heavily into
We
like.
should pay you cashews.
There you go. Look, I haven't gotten a new suit in 4 years.
I imagine that the
You need
people
to
that
pay me,
do
man.
the office
You don't get new
are
suits,
usually
you get
not-
fine.
Tailored.
Tailored suits, yes.
See, it's
Well,
all.
now you got a union, so go and strike.
It's actually worse for us out in the union
There's obviously a good
too.
amount of time.
It's certainly
The
been
art
more
is
for
logo,
physics.
and the very specific words chosen to go.
Yeah. At least for this.
Yeah.
Next year they'll get that.
Yeah.
I've done a triangle.
Years.
Yeah.
I'm gonna go
Guys
change
that break
my
legs.
Twitter background.
Well, that's, I always think the same thing that if you're gonna have a union.
Only the
those
real
three
ones.
Affiliated.
Everyone else will be
The
like.
guys that break the legs,
Break
right?
the
They
leg.
don't come in for this half-ass.
No, yeah. You gotta go all in.
You know, you gotta go all in.
So we should do it.
You know, even the mafia.
We're going to all of you, are they like your friends or? So I don't have friends.
Well, there you go, there's.
Well, I mean, the mafia,
That
yeah.
union enforcer.
The union enforcer, your football coach. And
They didn't get
There you go.
all at the same time.
Sounds like a good.
There's 70, yeah, 5%.
Say hello to the students for me.
Oh, like.
I'll see you around.
Randos, yeah.
Okay. Most people, I don't know. Anything are people, you know.
Yeah.
Like
Oh, yeah, there's quite a number of bots.
You guys are influencers. Yeah, random people you don't know are following. That's what an influencer is. Not when it's a bot. Not when it's a.
It's sad though, because a lot of the good people who are HC followers left. Yeah. Twitter's been, yeah. Why did you sign up to do the other things? No, that was right. No, I mean, I like just barely started using Twitter when you bought it and started fucking it up. So I was like, God damn it, like, it was already such a threshold to like get me on here. But the problem is there's so many competitors. I don't think any of them is making significant. I think basically what happened was he bought it, fucked it up. A lot of people fled. Then they dispersed kind of evenly across several different options. And now it's just kind of fucked. It's not.
What other competitors are there? The only
It's
one I
like
know is Direct.
Blue Sky, Mastodon, Reds is the latest, that came like way later.
But it's
like,
really-
Mastodon is like kind of
mature,
crap and
yeah.
it's been around for.
Like in the sense that there's limited like functionality.
Oh, yeah, no, I think it's just Facebook trying to bandwagon.
Yeah, it's very.
Yeah, of course. Cause they're metaverse, they work. Yeah. Oh my god. Right, it's a metaverse. What happens when you're worth like $100 billion for like $10 million? Like absolutely shit that no one wants to use your flag. Oh, but they're getting lots of money, that's why. Well, Facebook stock is like. Oh, but it's going up. Oh, it has? Oh, that was. Are you invested in Facebook? Did you buy it at the dip? I wish. I thought about doing it. No, I wrote Facebook off. It was the beginning of 2023, right? It started like super crashing and burning. And I was like, yeah, I fucking do this. So it's okay. Huh. Maybe it's something. Okay, $15 million. Additional. That's in addition to our existing 2 million. It's a huge blow up. I don't know, I was really far away. I think it's at 50 million, right? Us, baby? 5 for you? Oh, 5 for me? 5 for everyone else. Yeah. So we're talking about a job. What are you spending your $5 billion? 400 posts. 7,000 students. Kate Hall instead of being Department of Physics or even Fine Theory Institute. Like Rob McGee's office. 600 students. The office is just the middle part. I just sit at a desk in the basement. Come minions and everyone screams like you said. Like from like a coliseum. Yeah, exactly. That would be not as a pains. I think that was the 10-year vision that they were selling. Heroes should have so much money thrown at them. But the senior folks just sit in the center, it's a large coliseum style. Venues and have all the subordinates shouting. That's how we instead of gladiator fights, they have like just fights on the chalkboard. All students are That's kind of how things happen sometimes. Yeah, depending on where you are now. And then the more senior people give the all their shit gets erased. Oh, that's pretty. And then the PI says, "Let me know if you need a letter for industry." So then, I guess HEPAC has to officially accept it or something tomorrow, or there's some vote or. Yeah. There's presumably some formal mechanism also for folks in the community to like support it, whatever that is. But it's like probably important to sign in. So that we get our money. That's from Parks and Rec. Yeah, that. You watch that? No, it's the twins that are like really annoying.
Oh, yeah.
She's just like,
Yeah,
it's like, I forget her character. That's such an underrated show. It's a really good show. Yeah, hard. Not as good as you are.
Highly rated.
Is it? I had never heard of this before. Yeah, it's quite good. The Office, yeah, that's hard anyway.
Yeah, I feel like The Office is.
The Office is the absolute best show
Yeah.
ever written.
I think if you don't like if you want to see like happy shows rather than like terrible people shows, then like Parks and Rec is maybe a little bit more fun than The Office, but I think I like The Office.
Yeah, my wife strongly prefers those.
Yeah.
She's like, no, this is way funnier. This is way better. And I'm just like, it's an amazing show. And I love Amy Poehler and half the cast in there for sure. But come on, Scott's Tots. Hey, Mr. Scott, what you gonna do? What you gonna do? Make our dreams come true. So, I hate that. That's such a good one. And they're like on the phone back and forth with like Aaron and like Pam, and she's like, "You have to make him tell it." Okay. And at the end, he's just like, "I have hard drives or like whatever, like external hard drives." Oh, batteries! Batteries.